So good afternoon, everybody. This is Robert Franke from Likat in Rostock, and together with my colleague Schaubik Das from the University of Antwerp, I welcome you to the 7th event of the Sustainable Chemistry Lecture Series. Unfortunately, our colleague Adam Slabon, the third organizer of this event, cannot be with us today due to a medical incident. So this time again, we on the other side have two excellent guest speakers. It's my pleasure to welcome Shannon Stahl from the University of Wisconsin-Madison in the United States, who will educate us about the opportunities in the field of conversions with molecular oxygen. Our second guest is Dirk De Vos from the Catholic University Leuven in Belgium, and he will show us his latest advances in CH activation chemistry using microporous catalysts. So before we start with the scientific program, I'd like to make a few announcements. So the next event, actually the 8th event of the SCLS series, will take place on the 8th of September at 4 p.m. We will have a heavy focus on biomass utilization that time. So our guests will be Marcos Antonietti from the Max Planck Institute for Colloidal Research and Interfaces in Potsdam. Our second guest will be Erwin Reisner from Cambridge University. Some further remarks. So I would like to thank UCHEMS and KVCV, which is the Royal Flemish Chemical Society, for supporting our lecture series. A very special thanks goes to Thomas Franken, who's also here today from KVCV, for the fantastic technical support and for helping us in organizing these events. Finally, a last remark. So I would ask all the participants to use the Q&A box or the chat for posting questions to the speakers for the discussions later on. So I stop this presentation. In the meantime, Shannon, you can make yourself ready. I will introduce Shannon Stahl now. So this is our first guest. Shannon Stahl is currently a full professor in chemistry at the University of Wisconsin in Madison. Shannon received his bachelor's degree from the University of Illinois in Urbana-Champaign before he moved to Pasadena in California to carry out his PhD studies on alkane activation using platinum complexes. And this was done under the supervision of John Burkow at Caltech. Then Shannon moved back to the East Coast and worked as a postdoc in a group of Stephen Lippard at MIT in the field of enzyme catalyzed reactions. Afterwards, he started his independent career at the University of Wisconsin. And basically, he stayed there until today with a very few exceptions. For example, he spent a couple of months here in Rostock at Likat as an Alexander von Humboldt Senior Research Fellow, a very prestigious award. But this was long before I started. In the meantime, Shannon has built a broad and impressive research portfolio in the areas of catalysis, redox chemistry, biomass utilization, electrosynthesis, and electrochemical energy storage. For his achievements, Shannon received numerous awards. For the sake of our time schedule, I will keep this list short. I will mention only a few very recent ones. So recently, Shannon has received the ACS Catalysis Lectureship Award for the advancements of catalytic sciences. A few years ago, he achieved the American Chemical Society Award for Affordable Green Chemistry, as well as the EPA Presidential Green Chemistry Challenge Award. So before you become impatient, I rather finish now and hand over to you, Shannon. The screen is yours.
Okay, thank you, Robert and Schaubik and Adam, who unfortunately couldn't be here. I appreciate this opportunity to give this talk. I've seen the other announcements and admired what you've put together and appreciate this opportunity. Change my title just a little bit to try to emphasize one of the features that I'll be trying to address today. And so I'll be talking about catalytic reactions with O2 and showing the connection between energy conversion as well as chemical synthesis. But in particular, I want to focus on how thermodynamic considerations have often, at least in the way we began in this field, as catalysis researchers, we're almost always focused on kinetics and modulating, lowering barriers. And Until we got involved in electrocatalysis and thinking about electrochemical O2 reduction, the issues related to the thermodynamics of O2 reduction and then the kinetic processes related to that also have thermodynamic origins really weren't being accounted for. Let me move to this laser pointer. But this is a molecule that has fascinated me for many years, and so this is the focus. And maybe if there's just one thing to highlight here is just the different intermediates that can be involved in O2 reduction, all of which have different redox potentials, and that's one of the themes that will be coming up. Before I dive into the specific story, let me just give you the broader context of our interest in aerobic oxidation. So when we got started, we were focused primarily on palladium and O2 chemistry, so homogeneous palladium catalysis. In particular, the role of ligands in modulating the redox behavior of the palladium catalyst, controlling selectivity, reactivity, stereoselectivity, chemoselectivity, et cetera. Then we transitioned a few years later and added a focus on copper chemistry, specifically trying to understand how transition metals that are prone to one electron redox chemistry can mediate efficient 2 electron redox reactions using a 4 electron oxidant. And so all this incommensurate redox chemistry is a fun playground for mechanistic work, but also has broad implications for practical utility because of the use of non-precious metals. In the context of doing copper chemistry, we then paired it with organic nitroxyls, and we have a program that involves organic nitroxyls as well as quinones, and taking advantage of what enzymes often do is using redox active organic molecules. These can often be very efficient partners in aerobic oxidation catalysis. And then as a complementary program, we've been starting to work more in the domain of heterogeneous catalysis, trying to understand the synergies between homogeneous and heterogeneous catalysis. A few of the more practical applications focus on biomass. So in particular, focusing on lignin oxidation. It's not a story that I'll spend any time today discussing, but this is an opportunity to generate value-added aromatic monomers. So using lignin as an aromatic feed source of chemical feedstocks, aromatic feedstocks. And all this redox chemistry involving O2, of course, has strong synergy to electrochemistry, because what you're going to see is that ultimately almost all of our aerobic oxidation reactions feature the partnership of 2 redox half reactions, much the same way that you might consider in a fuel cell or an electrosynthetic apparatus. And so we have complementary programs thinking about electrochemical synthesis and also electrochemical energy storage and conversion in the same, basically trying to leverage our thought process as we kind of bring together 2 half reactions. From the practical vantage point of aerobic oxidation, I think it's worth noting, and much of, if I just jump back 2 slides, a lot of our work has been done in collaboration with the pharmaceutical industry. And this is, the reason this is worth noting is that if you think about aerobic oxidation catalysis, the vast majority of practical applications have been up here in the commodity chemical space, where O2 is really the only conceivable oxidant because of waste considerations and cost. And when you get in, and often in gas phase processes as well, when you start getting into liquid phase chemistry, this becomes more problematic because of the hazards associated with combining gas phase oxygen and liquid organic solvents. And so historically, this has largely been avoided. And part of our motive in getting into this space was to try to bring the features of enzymatic chemistry, but also heterogeneous catalysis and other ways of utilizing O2 to bear on liquid phase aerobic oxidation catalysis. And this was the basis of this book that I co-edited with Paul Alsters, at the time DSM. And just to bring some context to this, part of a consortium that we had a number of years ago focused on the safety aspects. And so this is something that will not go away. Obviously, safety has to be addressed when combining oxygen with organic solvents. And so one of the things that we did was to spend some time actually thinking carefully about what the limiting oxygen concentrations are as a frame of reference for thinking about aerobic oxidation reactions in organic solvents in liquid phase, and how tube flow reactors can actually facilitate practical implementation in these smaller scale operations. Okay, so what I show on the slide here are three completely different domains, historically at least, where you think about enzymatic catalysis, homogeneous oxidation catalysis, and fuel cells. And the primary the priority in this slide is really just to highlight the synergies, because each one of these is simply the combination of two independent half reactions, an O2 reduction half reaction combined with some substrate oxidation. And in a fuel cell, this is just hydrogen in a conventional fuel cell. But nonetheless, and here the priority, of course, is to generate energy efficiency for electricity production in a fuel cell. And so you're looking for very efficient O2 reduction reactions and hydrogen oxidation reactions to maximize the cell potential to generate that electricity. And the priorities when you get to homogeneous catalysis are actually somewhat different. Here, the goal is less about energy efficiency, and it's really about selectivity. And you could argue that rates and efficiency from a kinetic standpoint are important. But a lot of it really comes down to, can you use O2 as an oxidant to drive a selective oxidation reaction? And so that's been the consideration. And let me just put this in some context. So there's a long-standing history. Bachval has written a nice review. In fact, I should put up a new review that just came out in Angewandte on a similar topic, basically an update of this original 2008 article, talking about how homogeneous catalysis often benefits from redox couples that are partnered together. So these redox cascades, if you will, utilizing O2 at the end. And this just reflects the challenge of engaging O2 efficiently and selectively in these reactions. It often can be beneficial to bring in these redox couples. And if you think about it from an energy standpoint, it may or may not be useful, because every time you drive one of these half reactions, you necessarily are going to try to achieve a thermodynamically favored reaction. So you're losing the driving force available from O2 in doing this. But nonetheless, from a practicality perspective, often it's these redox couples that partner. And part of the focus of today's lecture is really to ask what might be the motive of doing that, and what are the principles, kinetics and thermodynamics, that underlie redox cascades of the type that are shown here. And I just draw your attention to the electron transport chain, which is obviously a feature of biology that in some ways mimics, well, we mimic biology more accurately, but the idea of having soluble, diffusible redox couples that capture the redox energy, if you will, for example, from NADH or FADH2, to drive O2 reduction, ultimately driving the proton transport and then ATP synthesis. But the idea of using these redox couples in these types of cascades in catalysis or energy conversion. Maybe just staying on the energy conversion theme, I'll just draw attention to something that just shows kind of this molecular thinking as it relates to energy. And this is the idea here, is that the same concept that you're seeing in homogeneous catalysis, you can actually use to drive a fuel cell. So the idea is you just like in a flow battery, you can use redox couples like quinones to do the electron transfer at the electrode. And then you can do the O2 reduction off electrode. So the ORR, the oxygen reduction reaction, doesn't necessarily need to happen on the electrode surface. The whole point is that this same kind of redox couple that you see in biology or you see in homogeneous catalysis can actually have bearing in energy conversion or storage. And this is a principle that may not find ultimate practicality in displacing conventional cathodes in fuel cells. But it was a valuable playground to start thinking about how mediated electrochemistry can be used for different types of energy conversion as well as chemical synthesis applications. This just shows a few of the details, kind of showing the kind of membrane electrode assembly that's used, where you essentially flow a solution of quinone through the cell, and the reduction of the quinone then leads to a hydroquinone that reduces O2 off electrode in a heterogeneous catalyst. So I won't dwell too much on this. This is part of our energy conversion scheme, and there are, I think, opportunities beyond ORR that may be more impactful in a practical sense. But this was one of the early implementations of this concept. So with that context of fuel cells, though, I think it's a nice segue into kind of asking the question about thermodynamics of O2 reduction and kinetics. And obviously, there's a strong interplay between thermodynamics and kinetics that come to bear, especially in fuel cells, where you're trying to drive the O2 reduction reaction as close as possible to the thermodynamic potential of O2, because that's going to maximize your cell potential and give you the most efficient fuel cell possible. So what you really want is to carry out O2 reduction at 1.23 volts. And that's just not possible because the kinetic barriers associated with O2 reduction are such that you need a catalyst. That's perhaps obvious, but that these catalysts have kinetic barriers that prevent you from operating at the thermodynamic potential. So you just cannot operate efficiently. There's no net current that you can pass if you would poise your fuel cell cathode at 1.23 volts. And so that would be akin to being up here on this plot. So this is a polarization curve for a practical fuel cell system. And what you find is that on the y-axis, you actually have to move that cathode potential down, and you actually don't start to see any current until you get to about 0.95 volts. And then real current actually, so the onset potential means you barely have any current. And as you drive the current, so this is essentially your rate parameter. So this is akin to a linear free energy, or not a linear, but a rate correlation, driving force rate correlation, where if you think about the voltage, that's the driving force, and then the rate is manifested as a function of the net driving force. And so what you find is that you need to go to higher driving force than would be ideal. And this allows you now to kind of change the energetic landscape so that you can actually get current to flow in your fuel cell. And all that basically means, and platinum is one of the world's best catalysts, and so it operates with an overpotential, meaning you have to drive it about 300 millivolts below the potential of the thermodynamic potential. So that's wasted energy. And I want to kind of think about that concept as it relates to aerobic oxidation during the course of this talk. But I want to also put it in the context of fuel cells, because essentially what we're doing, we're using O2 as an oxidant here. We're oxidizing hydrogen, which is obviously not of synthetic interest. It's all about energy conversion. But formally what we're doing is we're using O2 as the oxidant to drive hydrogen oxidation. And what we see is we have to waste a little energy to do that, and that's because of the kinetic barriers associated with this challenging 4-electron reduction reaction. Let me just try to bridge this a little bit further. Often, when you don't always study catalysts in an actual fuel cell device. In many cases, you're doing this at an electrode, where you're just looking at the efficiency of O2 reduction. And so this is a very common technique in this field of fuel cells, where you're looking at different catalysts using a rotating disc electrode. And what you do is you're rotating this electrode very quickly for the purpose of enhancing mass transport. And what you see is that this is the onset potential. So I kind of want to show you these two plots because they're essentially looking at very similar phenomena, where here you're looking at the cathode potential as it relates to the rate of the overall fuel cell, the current that you're flowing in the fuel cell. Here, you're just looking at the O2 reduction reaction. And again, you're starting at kind of up here would be 1.23. That would be the thermodynamic potential. There is no current at that point. You get to a point at which you now start to see an onset potential. Now you start to see some current. And then what you see is it plateaus. There's a mass transport limit. And so as you rotate this faster and faster, you can overcome that mass transport limit. But technically, let me just kind of walk through a couple of these regions, because this is kind of where you have the kinetic barrier. So you're essentially seeing this exponential relationship or logarithmic relationship between the potential and the current. So the driving force of the thermodynamics and the current. So, synthetic organic chemists will often use Hammett plots, and they'll plot log of the rate as a function of some electronic parameter. That's all this is essentially a rate driving force correlation. And so what you see is this kind of exponential relationship here, kind of in this region of the curve. And so the catalyst onset, that's where you see onset is when you finally get enough current to actually, you can overcome the barriers where you've added enough driving force by lowering the potential. So your electrons are energetic enough to kick off the reaction. Now, this value, this overpotential, changes the function of the current. And so, if you want higher current, you're going to need higher overpotential. And that's partly what this reflects. What I show in this line is kind of the theoretical curve that's not limited by mass transport. So that would basically just continue to come down, and the current can go through the roof as you go through as you lower the potential. So that's essentially without the mass transport limit. And so you reach this limiting current is really controlled by just access of oxygen to the electrode. So that's O2 reduction from the perspective of heterogeneous catalysts and fuel cells. Let me try to translate that, because there's a whole other world of researchers that we've been a part of thinking about molecular catalysis for O2 reduction. And so these are often in metal macrocycles or pseudo macrocycles like iron and cobalt complexes. There's a little bit of a difference when you translate from this Toffel relationship that we talked about here. This is the log of the current is proportional to the overpotential. So because of the electronic state of these catalysts, you essentially get this continuum, this exponential relationship associated with the current and potential. Molecular catalysts are somewhat different. Molecular catalysts you can think about them as being quantized. These catalysts do not work until you get to a particular redox state of the catalyst. So you go from cobalt 3 to cobalt 2, or you go from iron 3 to iron 2, and then catalysis turns on. And then those catalysts will turn on, and as you lower the potential and you overcome this exponential relationship as you're driving your catalyst from the cobalt 3 or iron 3 state to iron 2, that's this population of the catalyst. And so you reach people like Savient and Constantin and Jim Mayer and other many people are studying this kind of phenomenon, and so we've been part of this community. And so you populate your reduced state, and then it reaches a point where all of your catalyst is reduced, and at that point it's now going to be controlled by the chemical steps. And so this is not an O2 mass transport limit like you had here. Now it's controlled by the chemical steps. And so the purpose of this plot is to show that when you deal with molecules, rather than having this kind of a continuum of electronic states, you now have a quantized redox state where you're dealing with cobalt 3,2 or iron 3,2. And so you go from an off state to an on state, and then it's now controlled by the catalyst speciation. That being said, you can still, so now if you wanted to kind of look at this linear free energy correlation, and this is now maybe more similar to what we're used to in, say, organic chemistry, you see a log of a rate versus some thermodynamic parameter. So this would be akin to a Hammett correlation. It's just rather than using a Hammett a parameter, we're going to use the redox potential of the cobalt. So we can make different cobalt complexes that will have different cobalt 3,2 potentials. And what we see is that the rate follows a logarithmic relationship with respect to the redox potential of the cobalt catalyst. That linear free energy correlation is much akin to what we would see if we had linearized this exponential relationship shown here. It's just a different origin, because now what we have to do is we have to change the cobalt complex in order to get to a more reducing state. And yet at the same time, what we're doing is we're making a more and more reducing cobalt complex, and you see this kind of linear free energy relationship. If there's a take-home message from this discussion, I just want to make the point that the molecular catalysts are quantized. The redox chemistry, this overpotential that we talk about relative to the thermodynamic potential of O2, this overpotential is a quantum state. It's not in the same way a Toffel relationship that we see in heterogeneous catalysts. And so that's what I want to bring to bear now on synthetic catalysis. Okay, so let me try to make that transition to homogeneous catalysis. Because what you have here in a redox cycle of this type is a homogeneous catalyst that's shuttling between two different redox states. What that means is that we could think about each of the half reactions associated with this type of a redox cascade, if you will. The O2 reduction will have some thermodynamic potential, and that will be dictated by the potential of the catalyst that leads to the reduction. Then your catalyst, whatever its redox potential is here, will now have a particular driving force. So you will lose some potential from O2. So, a common question that I ask first-year graduate students is, is O2 a strong oxidant? And the real answer is, well, it depends. It depends on how you reduce it. And so the idea is that depending on the redox potential of this catalyst, O2 will either be a strong oxidant or a weak oxidant. And I show that over here. So the idea is that if you have a catalyst that has a high redox potential, this ECAT1, this will make O2 a strong oxidant, not because, of course, it's got its intrinsic thermodynamic driving force, but of course, it's only manifested when it actually oxidizes the catalyst to the oxidized state. So you essentially, the only amount of driving force from O2 reduction that you get is what's relayed into that catalyst. And so that can be shown here in this type of an energy diagram, where the catalyst, in this case, is a strong oxidant. Now, there are other cases where your catalyst will not do a good job of O2 reduction. It'll be a poor ORR catalyst. That means that your catalyst may sit down here. So it's got very little driving force then to relay into substrate oxidation. If there's a message that I'm going to come to by the end of the talk, it's going to be that sometimes you want a catalyst that is a strong oxidant. Sometimes you want a weak oxidant. Stronger catalysts will be able to access reactions that are difficult because it's got more driving force from O2 to drive that reaction. Catalysts that have low potential, you may be willing, because of the, say, environmental benign properties of O2, making water, you may be willing to waste that energy for the purpose of having a catalyst that now is very close to the substrate redox potential. As long as your kinetics are good, you may prefer to have a low driving force because that could confer chemoselectivity. Because you're not hitting your substrate with a sledgehammer, you're giving it a little soft touch. Basically, your catalyst is a very mild oxidant and now can kinetically efficiently oxidize the substrate. So as a molecular catalysis person, thinking about aerobic oxidation, I think it's worth thinking about kind of the overpotential from catalyst to substrate, but also the catalyst to O2 and how you manipulate the O2 a driving force as an oxidant. So just to summarize, you've got O2 that has a theoretical limit of 1.23 volts. Of course, we know the world's best catalyst still has an overpotential, so you're not going to get 1.23 volts as a driving force from O2. You might get, 0.9 or 0.95 volts. But we also know that molecular catalysts, at least the ones that have been reported thus far, generally fall in this range. In fact, I should probably stretch this all the way down here, because the way molecular catalysis researchers work is we don't care as long as we get good rates. Sometimes we keep driving the kinetics faster and faster. Well, one of the things that we've learned is that there's a correlation, right? I showed that on the previous slide. So of course you're going to get faster rates if you go to stronger driving force, but that becomes somewhat meaningless if you're really thinking about efficient O2 reductions. You'd like to push this gray bar over here to the left, because that would mean that you would have more thermodynamic capture of the driving force from O2. Okay, another final point before I leave this slide. If your catalyst makes hydrogen peroxide, you're going to be capped at a driving force of 0.68 volts. Okay, so the mechanism of O2 reduction here at this reaction matters, because you're not going to be able to capture any of this if you're ultimately reducing O2 to water or to hydrogen peroxide. Okay, so let's consider that from the perspective of palladium oxidation chemistry, which is the topic that we've studied the longest time. And generally, we've focused on reactions that couple with O2, and most of these cases actually function through a palladium-2, palladium-0 redox cycle. Okay, so one of the first papers we published as a group, actually was the first paper we published, was this characterization. So Electrochemical at the time had been looking at this batho-cuprin ligand on palladium as a way of actually making hydrogen peroxide. In a biphasic system, they were using various reductants like CO and alcohols and hydrogen, and trying to use this as a method for direct production of hydrogen peroxide in water, but using the ligand and catalyst in an organic phase. So the hydrogen peroxide would partition into the aqueous phase. So seeing some of those papers at the time, Roger Sheldon had some beautiful work on aerobic alcohol oxidation too, using a phenanthroline ligand not too unlike this. And so we said, how is O2 reacting with palladium-0? So we did some more inorganic focused chemistry here and showed that this made it hydrogen peroxide, which was not unexpected based on the Electrochemical work. But let me just kind of bring that to bear on the topic here. What that means is that we are making hydrogen peroxide. So when you're doing this palladium-2,0 redox cycle, you're going to be limited to 0.68 volt driving force. So that's basically all you're going to be able to access as an oxidant and using O2 as an oxidant. Why does that matter? Well, let's consider reactions that will, here's a beautiful story from Dirk De Vos later, but I'm going to put it in the context of this bi-aerocoupling, say making biphenyl with O2. And I'm not going to tell you about the development of catalysts for this process, but I want to consider this problem of making biphenyl versus making phenylacetate, which is a phenol precursor that many people have long wanted to do, using very similar types of palladium chemistry with the idea that the palladium-2 could undergo CO bond formation. And one of the things we did that I don't spend time in this talk describing is, this CO reductive elimination from palladium-2 is very slow. It works better, of course. Beautiful work by Melanie Sanford and other people in the community have shown that if you go palladium-2,4, you now can undergo reductive elimination of a CO bond to make phenylacetate. Of course, we don't want to use hypervalent iodine in these cases. We want to use O2. And so generally what you see is that these palladium-2 areals will undergo a transmetallation or some other mechanism to afford biphenyl. And the question is why? Why is it going to biphenyl instead of phenylacetate? Well, the simple answer is CC reductive elimination is easier than CO reductive elimination. But let's think about this more from a thermodynamic perspective. So these are the two reactions. And if you go to NIST database, the National Institute of Standards that basically provides thermodynamic data, you can get a pretty decent approximation for the thermodynamics of these reactions. Now, these are kind of all using standard states and the kind of data that you get at NIST. But what you find is that the free energy here is almost ergo-neutral. So there's not much driving force. You should almost be able to drive this reaction just by eliminating H2. You shouldn't even need an oxidant if you've got some efficient way of sweeping out the H2 as long as this reaction is kinetically efficient. In contrast, making phenylacetate or phenol, this is quite a bit uphill, right? You're never going to drive this reaction making H2. And so you're going to need an oxidant. So I translate these free energies into standard potentials. Okay, so that's just delta G equals minus NFE. So we can just run the equation. You can get a thermodynamic potential for this relative to hydrogen production, the H2 H plus redox couple. And what you find is that the E naught here is close to zero, close to the hydrogen redox potential, which is obvious because we have almost an ergo-neutral reaction with respect to hydrogen production. Whereas this one is 324 millivolts uphill to make phenol. And that was my placeholder because that's where the thermodynamic data were available. So I put this on an energy diagram. So here are the redox potentials of the benzene to biphenyl and benzene to phenylacetate at 0.01 and 0.32. In fact, this looks like I botched this. This should be a little bit higher because that's almost at zero. But what I want to convey is that the mechanism of palladium-mediated oxygen reduction is going to dictate the driving force you have available for substrate oxidation. And what I just showed you is that palladium-02 often goes through hydrogen peroxide. That means that you have a driving force of only this value to drive, that's associated with this redox couple. The question is, that assumes that whatever hydrogen peroxide redox couple is perfectly related into the catalyst, and that's almost certainly not true. The question is, what is the palladium-2,0 potential? And we don't know. In most cases, we have no idea. In fact, this was actually a study that we just published. It was actually the first reported redox potentials for palladium-2,0 because you can't just go get a cyclic voltammogram of palladium-2,0. So it's a horribly irreversible redox wave. But by using this potentiometric method, using benzoquinone, hydroquinone as a couple, it turns out that we were able to benchmark some redox potentials. Now, it gets complicated, and so it's not as simple as just measuring some redox potentials under one set of conditions, because conditions matter. But what I want to convey is, depending on the ancillary ligand that you place on your palladium, you can have a very different redox potential for your palladium-2. So palladium-2,0 is not a fixed redox potential. It's very dependent on the ligand, as one might expect. And this was the first time these numbers had actually been documented. But I just come back here. Truth be told, we don't know what the redox potential of our catalysts are under these conditions. And that's a complication. But what I can say is by virtue of the O2 reduction reaction, we know that we can have no more than 0.68 volts as a driving force to drive these reactions. Okay, and so depending on the kinetic barriers, you're going to have an energetic loss here. So this is probably less than 0.68 volts. And then that's going to have to be relayed to the substrate. And so you may have very little. In fact, what I'm trying to convey here is you may have palladium-2 zero redox couples that are actually not thermodynamically capable of taking benzene to phenylacetate. And I don't think that's something that many of us in the community have thought about in the context of aerobic oxidation chemistry, is kind of thinking about this from this thermodynamic perspective. And it's only something we're now starting to think about thanks to kind of starting to focus on ORR and then energy conversion perspective. Okay, so if we come back here, this just kind of wraps up this little subplot. This is the story. If you wanted to make phenylacetate, it doesn't happen, because what happens is that the palladium-2 aerial just reacts with a second arene, and there's various mechanisms for that. One that we characterized was a transmetallation pathway, but there are others. And so you can make biaerials more efficiently, in part because you don't have a good mechanism for getting O2 to react with palladium-2. Okay, so, as I mentioned, palladium-2 zero makes hydrogen peroxide. How in the world are you going to get O2 to react with palladium-2? Most likely, it's going to bind as a superoxide. Well, superoxide has a redox potential of 0.15 volts. So, it's just the kinetic pathways for oxidizing palladium-2 to palladium-4 with O2 are just problematic. We'll come back to that story. Now I want to shift gears. So I've told you about this palladium-2 zero redox couple. I want to focus instead on this nitroxyl hydroxylamine redox couple. So what we have in this case is a reaction that generally is used in this case for alcohol oxidation. But we started asking the question, how should we think about this O2 reduction reaction? Because using O2, going to NOx, going to tempo, going to alcohol oxidation. And we wanted to characterize the thermodynamics and kinetics associated with this O2 reduction reaction. So we said, let's just scrap the organic substrate for the moment and focus on using an electrode. Now, the reality is why do you need two co-catalysts? Okay, and that's a worthy question. In principle, the net goal is O2 reacting with alcohol, and we know that you're not going to do a good job if you just combine alcohols. Alcohols, just like human bodies, are stable in the presence of O2, even though they're thermodynamically unfavorable with respect to combustion. Okay, but you start putting in catalysts and you start asking the question, what catalyst is doing what? Well, we know tempo is a good substrate catalyst for alcohol oxidation. We also know that hydroxylamine will slowly auto-oxidize to make tempo radical, but it does not make oxymonium in the presence of O2. So tempo, what you buy from Aldrich or your favorite chemical supplier, is going to be in the organic radical state. So the aerobic stability, you just don't have a good kinetic pathway for O2 oxidizing to the oxymonium. That being said, these reactions are driven by O2 using NOx. This was just to convey that you can go from here to here, but not all the way up. Okay, so what's beautiful about NOx is it's a pretty remarkable redox couple, because nitric oxide reacts with O2 efficiently to make nitrogen dioxide. Then nitrogen dioxide can undergo proton-coupled redox reduction to make nitrous acid, and nitrous acid can undergo proton-coupled reduction to water and nitric oxide. And note the redox potentials here, 1.09 and 1.0 volts. So the average would be 1.05. So going from nitrogen dioxide to nitric oxide has a redox potential of 1.05 volts. That's remarkable, as I'll try to convey. So first of all, the question might be, why not just use NOx itself? And the reality is, because it's kinetically problematic for outer sphere electron transfer. So it does not do good electron transfer at an electrode. This is evident from the self-exchange rate for nitrite and nitrogen dioxide. And if you try to do CV with nitrogen dioxide, it's just horribly irreversible. So these are overpotentials that are associated with the slow electron transfer that you have with the NOx-based species. Put that in with tempo, and all of a sudden, and this just shows the difference between doing a NOx-only reduction of O2, and here are the currents that you get just by adding tempo to the same conditions that you had with sodium nitrite, which basically drops into the NOx chemistry. What you find is that you can now sustain good currents when you have both of these species present. Okay, so you need both of them. Let's just think a little bit why the combination of tempo and NOx plays a valuable role for O2 reduction here. Incidentally, one of the things we measured was the overpotential for this. That's 0.3 volts. That 0.3 volts is basically sitting right on top of platinum. In fact, it might even be a little bit better than platinum as an overpotential. It's not going to be a practical fuel cell catalyst, in part because these are gas-phase species. So you're going to have a hard time managing gases in a fuel cell if the catalyst is a gas. Nonetheless, what it shows is that NOx is extraordinarily efficient in this tempo-NOx redox couple in terms of capturing the thermodynamics of O2 reduction. Because remember, palladium, the story I just told you, said we're making hydrogen peroxide. So at best, we're getting 0.68 volts from O2 as an oxidant. Now, by using the tempo-NOx cycle, we're all the way up at whatever this is, 0.95 volts or is 0.3 volts. So just drop 0.3 volts down. So that'd be 0.93 as the driving force for O2 reduction. But let's just think mechanistically what's going on, because this is an amazing set of cooperative catalysts, right? Because we know that NOx has terrible outer sphere electron transfer. So we can't use the NOx cycle alone because of the slow electrochemical kinetics. We also know that tempo does not react efficiently with O2. So it's terrible. And so it's not going to do this cycle all by itself either. What we know is that tempo oxymonium is a very fast redox couple. There's a great, one of the most popular mediators by organic electrochemists is to use tempo oxymonium. We also know that NOx, nitric oxide, reacts rapidly with O2 to make nitrogen dioxide. So that redox couple is fast. The implication that all this works is that tempo and nitrogen dioxide also react efficiently. And we can show that independently by UV-vis studies, for example. And the implication is that there must be an inner sphere pathway for this, because we know outer sphere electron transfer with NOx is slow with nitrogen dioxide, but that's a radical. That's a radical. So odds are there's an inner sphere pathway that makes this step fast. So by putting these two species together, you essentially eliminate all of the slow steps, turn on all of the fast steps, and now you have efficient O2 reduction at a very, very low overpotential with these molecules. Okay, basically equivalent to the world's best catalyst for oxygen reduction, which is platinum. Okay, let's continue on the tempo theme. So I'm going to shift gears now, thinking a little bit more like an organic chemist. So if we wanted to think about alcohol oxidation, we could bring these concepts to bear on alcohol oxidation in a variety of ways. And there's a lot of interesting possible reactions involving alcohol oxidation. I won't go into all the details. This hydroxylamine oxoammonium redox couple with NOx is actually very practical. This is something we developed in collaboration with Eli Lilly. They've actually run this on scale, not the ABNO. They actually ended up using a tempo just for the cost of the oxymonium cycle. But this is actually a very good redox couple for alcohol oxidation, with a catch. The oxoammonium turns out to be incompatible with many functional groups, but we'll get to that in a moment. Shift gears, this tempo system is one of our cooperative catalyst systems. So this is building on some seminal work by Marty Semmelhack and Roger Sheldon. Also, Koskinen had developed some work almost contemporary with us. So this is a very practical catalyst system as well. In fact, it's in some ways the most effective catalyst for alcohol oxidation, is now being adopted by many synthetic organic groups who are making complex molecules because of its effectiveness. We had an interesting kind of serendipitous discovery that when you combine copper-1 with tempo rather than copper-2, that the chemistry really kicks on. And this turned out to be the most practical version of the catalyst system, was starting with a copper-1 salt. And I just draw attention to the broad functional group compatibility that you see here that really extends even beyond what you would get from a tempo oxymonium pathway, this copper tempo system. Also, it shows good steric activity, so you get very selective oxidation of primary alcohols. I just show you here, for example, the primary alcohol. To make this lactone, you're oxidizing this aliphatic primary alcohol, even though this is secondary and benzylic, which is kind of a doubly activated site. You get lactone that all reflects the steric control of the primary alcohol. Anyway, I don't want to get too far into the synthetic direction. But to come back to mechanism. So there was a question about what's the mechanism. So one of the possibilities is that copper-2 is just oxidizing hydroxylamine. So this was what was originally proposed for this catalytic mechanism. And without showing all the data, I'll just cut to the chase. This pathway is very much akin to what you see in galactose oxidase, where you have a copper-2 and an oxyl radical working in partnership to do alcohol oxidation in this sequence. So this is a 2-electron oxidation that uses 2 1-electron oxidants. So you're not actually going up to the oxymonium. So this is not involved, but rather using tempo plus copper. Now, maybe this is a chance, I forget if, I mentioned that we found the use of a copper-1 catalyst was really effective. The reason, in principle, you're going through copper-2 and copper-1, so why should it matter which redox state you start with? It turns out that the reason this is valuable to start with copper-1 is that the reaction of copper-1 with O2 to initiate the chemistry generates a base in the coordination sphere of copper-2. And that means that you can essentially engage your substrate with the base that you've installed from O2 reduction. This is not unique to this system. We've seen it in a number of other copper systems where if you start with copper-1 and reduce oxygen as the initial step of the reaction, the installation of base into the copper coordination sphere actually engages substrate effectively and turns over the catalyst very, very well. The main point here, though, is the joint cooperation of 2 1-electron oxidants bypassing the 2-electron redox couple hydroxylamine to oxymonium. Let me just briefly highlight the mechanism of this reaction. So the mechanism involves this 6-member transition state that's shown here. It turns out these are computations that basically show that justify why when you have a secondary versus a primary. You can see the barrier to this reaction is higher when you have secondary alcohols versus primary. The other thing that may be worth noting is that the primary barrier in this overall reaction is actually getting the nitroxyl to dock onto copper-2 to generate the cooperative catalyst. That makes sense because tempo, is a mild oxidant, right? We often use it as a mild oxidant or an HAT reagent. Tempo is not, ligands are supposed to be electron rich, right? The reason they bind to metals is because they got electron density that binds. Well, tempo is an oxidant. It doesn't want to bind to copper. And so the major barrier here is actually getting tempo on. And then you can see transferring the hydride is almost barrierless when you don't have steric effects in this chemistry. It may be worth noting, this is basically like Oppenauer oxidation with a driving force, right? So the Oppenauer oxidation is just a Lewis acid that mediates hydride transfer between a ketone and an alcohol. Copper here is basically playing the exact same role as this hydride acceptor down here, copper and nitroxyl. The only difference is that now we've got oxidants involved rather than some thermoneutral reaction. It's also worth noting that this copper nitroxyl adduct is also playing the role of a 2-electron noble metal. So rather than doing beta hydride elimination to a single metal, you're now taking advantage of the 6-member transition state to do what is formerly a beta hydride elimination to this 3-atom fragment. Okay, I think I want to speed up a little bit through the synthetic scope. We wanted to, so I'm going to maybe go a little too fast through these next couple slides. We wanted to develop a better catalyst because we wanted to be able to oxidize secondary alcohols. We thought about changing the redox potential of tempo. Turns out if you use a stronger oxidant in the tempo, it's no longer a good ligand. And in fact, it works worse. What works best is actually changing the sterics. And so what you find is this abno works remarkably well with all manner of substrates. What you see here is the chemoselectivity, especially well with primary alcohols. These secondary alcohols are essentially unreactive. And so that's essentially showing that, whereas this abno without steric effects now oxidizes everything very well. This is manifested in the DFT calculations, which basically show secondary and primary no longer have a preference. In fact, there might even be a slight electronic preference for the green secondary alcohol if you believe those differences, which I think you shouldn't. But the point is that there's very much not a steric effect going on here anymore with this sterically unhindered nitroxyl. Okay. Finally, just with respect to synthesis, maybe if there is a point about the synthesis, it's the functional group compatibility. Note the presence of tertiary amines. In fact, it's been done, Iwabuchi has done some similar chemistry with primary amines and secondary amines. You can see free anilines in this system. You can see unprotected indoles. These are very electron-rich groups that many oxidants would annihilate. And yet this chemistry is very compatible with these substrates, which is part of the appeal and why the medicinal chemists were clamoring for a solution that they could just buy where they don't have to weigh out all the individual components. And so we ended up doing that and selling it through Sigma Aldrich. It's also been scaled. So a number of companies have now publications, but also anecdotal comments from companies that they can scale this because it really is a mild reaction and is compatible. You can dramatically lower the abnol loading, for example. This was a paper we published in collaboration with several companies focused on the process features. But let's come back to mechanism. And so I just want to highlight, these three redox states. What I've shown you in this copper tempo case is that copper tempo is taking advantage of just this low potential redox couple, not the high potential redox couple. Mechanistically, I show that here where you take advantage of the cooperativity of two 1-electron oxidants. Okay, what are the implications of that? Because we've seen two different nitroxyl alcohol oxidation reactions. One that goes hydroxylamine all the way up to oxymonium in a 2-electron step. The other, which only goes 1 electron to nitroxyl, then takes advantage of copper 1,2. Okay, so we hook those up to an electrode to assess their driving force for alcohol oxidation, anticipating that there should be a difference. Sure enough, there is a difference to the tune of about 0.5 volt. The copper tempo system is about 0.5 volt lower in potential relative to the nitroxyl. And if you actually use the electrocatalytic data and analyze the rates, what you find is copper tempo is like 5-fold faster than the oxymonium. This says that a weaker oxidant is actually functioning faster, and that undoubtedly reflects the mechanism of the alcohol oxidation, which just creates lower barriers and still has adequate driving force to drive the alcohol oxidation. So even though it's a 0.5 volt weaker oxidant, it's still driving alcohol oxidation to the tune of 5-fold faster than your conventional oxoammonium pathway. What does that mean? Let's just kind of look at that. What we basically have done is by combining copper and tempo, we've converted the nitroxyl copper system into a weak oxidant compared to a strong oxidant. What did that do for us? That conferred remarkable chemoselectivity. So now we can tolerate all those oxidatively sensitive groups. So in this case, you could argue that what we wanted to do was actually waste ORR potential, right? We don't want O2 to be a strong oxidant. We want to knock it down and turn it into a very mild oxidant, because now we get the broad functional group tolerance because we've got a very mild oxidant with low kinetic pathways, kinetic barriers. And so now we do very efficient aerobic oxidation with a very chemoselective, low driving force catalyst using copper tempo compared to oxoammonium. Oxoammonium is still a great catalyst, and so many substrates are fine with tempo. But what this means is that if you want functional group compatibility, you're probably going to want copper tempo because your functional groups, heterocycles, and other things are going to tolerate that at the expense of O2 reduction efficiency. But who cares? We're synthetic chemists. What we care about is the organic molecule, right? If we're driving a fuel cell, we really care about this, and we want to maximize the efficiency of O2 reduction. But if you're a synthetic chemist, you may not want to. In some cases, you may be more interested in the functional compatibility of a low over potential alcohol oxidation catalyst. What that means is I'm basically moving my oxidant down to the thermodynamic potential of the substrate. Instead, that's basically what's shown here. We're wasting all this driving force for O2 reduction so that we get this exquisitely tuned catalyst with a very mild, or hitting with a very soft touch is the way to think about it. Whereas this one is giving it a slug, in the gut, basically, and driving this reaction with a strong driving force. Okay. I want to end by just coming back to this palladium reaction, because again, O2 does not make phenylacetate. And the question is, can we change that? Well, I've just shown you a possible strategy. What we started with was by looking at palladium 02, we often make hydrogen peroxide. So we don't have much driving force available from O2. Well, let's use NOx. NOx as a redox couple will give us a much greater driving force. So can we pair NOx? And this is not new to us. This goes back to the early 70s and even 1969, where this concept was first introduced. But what we were able to do is actually achieve benzene to phenylacetate over 100 turnovers by using NOx. And keep in mind, what's basically happening, I mentioned O2 to superoxide. 0.15 volts. So if you try to dock O2 onto a palladium-2 center, there's just not the driving force that's going to get you anywhere close to palladium-3 up to palladium-4. Whereas nitrogen dioxide, 1.1 volts. You've got almost a volt extra driving force to kick this up into high gear, get it into palladium-4 so you can now make a CO bond. And so that basically says that by using this type of NOx redox couple, you can now access this palladium-2,4. And and I mentioned a number of groups that have exploited this in other contexts. Our interest was specifically in this benzene oxidation, but this kind of puts this kind of thermodynamic framework for why NOx redox co-catalysis is facilitating this chemistry. So just to bring this palladium story to a close, essentially what we have in the biphenyl, we're using hydrogen peroxide. We have a palladium-2,0 couple that's got enough driving force to make benzene to biphenyl. By putting in NOx, we now can access the palladium-2,4 couple, which is going to be higher than the palladium-2,0 couple, that now can make benzene to phenyl acetate at that higher substrate potential. So this is the substrate potential that we need to access compared to the 0.01 for making biphenyl. Okay, so anyway, you could imagine, just to kind of broaden the scope, this applies in principle to all kinds of substrate oxidation reactions. I won't get into them. We've got a perspective article that we're coming out with some of these documented that should be appearing hopefully in the next month or two. Okay, so this is the concluding slide. Conceptually is just, thinking about synthetic chemistry. For energy conversion, of course, you want to reduce the overpotential for O2 reduction to maximize the cell potential, right? We want this cell potential for hydrogen, which is very, very efficient, operates almost at the thermodynamic potential, but you want to move this up as much as you can, and that's been the goal of fuel cells for decades. And also the goal is to do it without having to use a precious metal. In organic oxidation chemistry, it actually depends. And I hope the take-home message you take away is, at least conceptually, thinking about this over potential for O2 reduction, over potential for substrate oxidation. You may want a catalyst that kind of sits down here very close to the substrate oxidation potential, so that you have a very exquisitely tuned catalyst with very good functional compatibility. You may not want to hit it with a sledgehammer in this way, with the large driving force. And so sometimes you want to expand the inefficiency of O2 reduction so that your catalyst, and it kind of comes back, if you remember the early part of the talk, these catalysts are quantized, right? You are sitting at a potential. So it's not a continuum. Your catalyst sits at a potential. So this line here is basically going to slide up and down depending on its redox potential for aerobic oxidation. So with that, let me thank my group. This is a story that's been evolving over the last 20 plus years, going back to my first postdoc in the group, and some of the early researchers started looking at CH activation and CH functionalization, some computation with Clark Landis. Copper tempo, Jessica Hoover was a postdoc who first discovered the copper tempo variant that used copper 1, and then a number of group members doing mechanistic studies as well as synthetic applications. James Gherkin has been a key player in our energy conversion and did much of the electrochemistry related to tempo NOx in addition to the mediated fuel cell. And then thinking about these thermodynamics, James has been working with some of our group members to document some of these thermodynamics to start putting this map together, because I don't think this is a common way for synthetic chemists to think about energy as it relates to synthetic utility. So with that, let me thank you for your attention and wrap up here.
Shannon, thank you very much for this very interesting and educating talk. And I really appreciate the unifying approach towards all these different applications. So I see no question at the moment in the chat. So I simply start while in the meantime, people can post the question. So I have a specific question regarding the fuel cells you presented. So there was this tempo NOx fuel cell, which consists basically of two homogeneous redox couples and oxygen in the half cell. And this, of course, so you've mentioned that the overpotential was in the same range as for platinum. So how about the stability when you compare it? And have you tried to improve improve stability if this is an issue with immobilization of the catalyst?
No, we have no interest. I'll be honest. This was a conceptual study for the purpose of understanding the thermodynamics of these homogeneous catalysts that are used for synthesis. There actually is a, it turns out that, I mentioned that the NOx redox couple is slow. Well, you can overcome kinetics, by, heating. And there was shortly after we published our work, there was an actual fuel cell using nitric acid alone, which will in situ generate NOx and then sustain aerobic oxidation. And the reality is that's never going to be practical, right? Because you've got a catalyst that's a gas, you're flowing your gas in, you're trying to manage water effluent, and there's no way to retain your NOx. And the last thing we need to do is to load up our atmosphere with more NOx. So I don't think it's worth trying to turn this into a practical fuel cell concept, except to the extent that you take the principles of identifying species that do efficient O2 reduction, which has been the goal of every fuel cell ORR researcher for the last, umpteen decades. So that's not new, but I think what is new is kind of the way in which this superimposes on the synthetic chemistry and thinking about how O2 reduction efficiency is translated to a driving force for chemical oxidations.
Thank you. So just sticking to the same system, so now you have made clear that this is rather a conceptual study, but nevertheless, I was wondering if one could switch the NOx by something more easily handleable, so something like the copper catalyst, for instance. Can you use the copper catalyst at this point, or some other redox couple?
Yeah. Okay. So it's clear that my presentation wasn't totally clear, because one of the things we showed with the copper chemistry was that we're now getting a very high overpotential for O2 reduction. That's good from a synthetic perspective because the catalyst now operates very close to the redox potential of the substrate. So it's a very mild oxidant, but it's a pathetic ORR catalyst. So you would, if you try to run a fuel cell with this type of catalyst, you would now have very, very almost negligible cell potential. So your energy efficiency would be terrible. And I guess I don't want to. I think that the connection to the energy field is important conceptually, but what I'm really trying to convey is how the energy perspectives have implications for synthetic chemists, because you need to think about kind of the redox driving force in the different half reactions associated with these reactions, because it has implications for chemoselectivity as well as driving force for more challenging oxidations like benzene to phenylacetate. That's, I think, yeah, just be aware. I mean, as you, I'm certainly know, there's a whole world of molecular catalysis for ORR, and so that would be the world that I would direct you to. There's dozens and dozens and dozens of papers, hundreds of papers in this space where people are looking at different molecular catalysts for O2 reduction. And those are the kinds of species that would be relevant. The focus has been, how do you lower the overpotential? And so some of the best catalysts are these cofacial porphyrins that Jim Coleman reported many years ago. Those are the ones that actually get to about 0.7 volts, but 0.7 volts is still far away from the platinum 0.95 volts.
Thank you. Shobik, you have a question.
Yeah, Shannon, thank you very much for such a nice, we have learned a lot. I have two questions, but two are very naive questions. So one is that often I hear from industry that they prefer hydrogen peroxide over oxygen. Of course, in our lab, we also work with oxygen to use as an oxidant or transformation like alcohol oxidation and some other things. So what will be your comment of using oxygen over hydrogen peroxide? So this is my first question. And my second question is, your copper catalyst for the oxidation of alcohol is phenomenal. Yeah, this is fantastic. The selectivity is outstanding, particularly for the aliphatic alcohol, which is more challenging. I mean, the aromatic alcohols or heteroaromatic, it's doable. But aliphatic alcohol in presence of the secondary alcohol, secondary hydroxy group is really challenging. So my question is there, can you also recycle the copper catalyst? Is it possible to use some heterogeneous catalyst? Because anyhow, your system is a tempo-based system, and then you recycle with oxygen, but can you replace it with some other, let's say, heterogeneous copper catalyst or other?
I'll answer the second question just very quickly. That's an ongoing challenge. And I would say these catalysts, when we talk to pharma, 5 mol% copper is not prohibitive for them. Sure. If they could use 0.1 mol%, they would love it, but they don't. That's not a key player because it tends to be easily washed away. That's not a good answer. The reality is this is still a research problem. we don't really understand why the catalyst dies and how it dies, and that's part of an ongoing, exploration across the community. The first question was, what about hydrogen peroxide? Hydrogen peroxide is an interesting beast because, when you go to the thermodynamics for O2 reduction, 1.23 volts, O2 to hydrogen peroxide is 0.68 volts. Turns out hydrogen peroxide to water is 1.8 volts. So it's a wicked strong oxidant. It also is dangerous because it will disproportionate. And so it depends on who you talk to, whether they prefer it. But what I can say is that hydrogen peroxide is actually a much stronger oxidant. And yes, it's nice because you can deliver it as a liquid, right? So it's more easily handled. What I would say is we don't know how to harness very well, meaning my group, and then I think more broadly, and this would be a worthy discussion over a drink sometime, is how do you get hydrogen peroxide to serve as just an efficient two-electron oxidant, as opposed to an oxygen transfer reagent or radical source or other things. Because it's such a strong oxidant, because the O bond is so weak, it often engages in unselective chemistry. And so that's why it can be used, like terbutyl hydroperoxide or diterbutyl peroxide are used for HAT chemistry, because that bond is weak and then you have a very strong oxidant available to do interesting chemistry. So that's a completely different field. That's a different, it's a different topic. Very interesting. I didn't talk about that part of my group kind of that's focused on kind of HAT chemistry. That's a separate topic though. And I think these are complementary applications that you'll probably encounter, where sometimes you want to use hydrogen peroxide or a peroxide-based oxidant. Sometimes you want to use O2. Understanding the nuances of when you want to use what and when, what's efficient. Let me just end with, we don't know how to do hydrogen peroxide reduction efficiently. And the moment somebody does that, there's going to be hydrogen peroxide fuel cells on the market, because we don't know how to do that, because you're actually well above the water oxidation potential. So this is a reversible potential at 1.23 volts. So if you have a catalyst that can reduce O2 or hydrogen peroxide to water, you also have a catalyst that oxidizes hydrogen peroxide up to O2. Okay, and so you probably have a good disproportionation catalyst. There's a whole host of complexities. And so at least right now, there's not good catalysts for hydrogen peroxide reduction that could then harness that driving force in interesting synthetic applications. So obviously, if you want to do epoxidation, these kinds of things, that's an oxygen transfer reaction. So that's a mechanistically different class, where there's a lot of interest on sulfoxide and other applications. So, but these are different domains of oxidation chemistry, and I didn't touch on that today.
Sure. Thank you, Shannon.
So we are a little bit behind schedule, but I think we should allow one more question. So this comes from Yongming Yo. So thank you for the excellent talk. Can you please comment on the ligand effect on the Palladium 2, Palladium 4 cycle? Is this a matter of the ligand stability, or is it less pronounced in those reactions using the Palladium 0, Palladium 2 couple?
Oh boy, I mean, obviously the ligand's going to matter, because the more donating, the easier it is going to be to get up to Palladium 2,4. But you've got to be able to somehow manage the Palladium 2 so that it's got to stay electrophilic, right? If you want to oxidize Palladium 2 to Palladium 4, you want a really donating ligand. But of course, if you make a really donating ligand, the odds are it's not going to be a good electrophile for CH activation or the other reactions. So there's all these interplays, and that's about maybe where I should stop. There's a whole discussion that we could have around that topic. But hopefully that gives just a general framework.
Okay, thank you very much for the discussion, and also thanks for the talk again. Now I hand over to you, Shub, and to continue with Dirk's talk.
Yeah. So after an inspiring lecture from Professor Stahl, we'll now move on to the application of microporous catalysts towards CH bond activations. And to understand this chemistry better, we have a very high voltage renowned speaker, Professor Dirk De Vos from KU Leuven, Belgium. As usual, we start with a brief introduction of our guest. So Dirk has finished his PhD in 1994 in KU Leuven, and then started as a postdoctoral researcher with a very prestigious FWO postdoctoral fellowship in Belgium. In 1997, he joined as a lecturer in KU Leuven, and since 2006, he is a full professor in the Department of Bioengineering at KU Leuven. It's quite obvious that his impressive CV, impressive research, and impressive output has earned a lot of awards, and it's obvious. However, in the interest of time, I am not going to tell all the names, but some of the names I'm going to mention. So he achieved DSM Chemistry and Technology Award, Donald Breck Award from the International Zeolite Association, André de Routre Award from Material Science from KU Leuven, BSF Catalysis Award in 2001, and very recently Vlaamse Wetenschappelijke Stichting Award in 2006. The main interest of his research group is to enrich the field of catalysis with zeolites, MOFs, and other porous or highly dispersed materials. So of course, some of them we will see today. And reaction-wise, the central themes of his groups are selective oxidation. So part of the things we have learned from Shannon, hydroxidations, particularly main focus towards renewable feedstock molecules, and CH bond activations. So with this information, Dirk, I would like to request you to take over the screen, and I'm very much looking forward to your lecture.
Thanks, Shobik, for this very kind introduction. I hope you can hear me and see my screen.
Yes.
Is that okay? Very fine. So first of all, thanks, Shobik and Robert, for inviting me to this symposium, and I'm very honored to be on the program together with Shannon. Actually, that's quite impressive for me. So thanks a lot for that. And I'm also very glad with all the people in the public, all the listeners in Belgium, at the University of Antwerp, but also outside Belgium. I saw many of my well-familiar colleagues from Sweden, especially Jan Beckval. Very fine that you're listening to us, Jan. Thanks a lot for your attention. But I'll kick just in with the chemistry. We have till 6 maximally, so I'm not going to speak for a too long time. I'm going to speak indeed about our adventures with solid catalysts for aromatic alkylation and arylation via CH activation. That's going to be the theme. It's all going to be palladium chemistry in many different shapes, forms, and so on. We are in Leuven, Leuven, the nice old historic town. This is the university library. This is the castle, which is quite close to us. And here you see a sketch of our new building. Actually, now the building is already reality. We're sitting somewhere at the back and doing our chemistry and enjoying that very much. The results that I will show today are mainly originated from the PhDs from Niels van Veldhoven and Jannik Verkammen, but of course, many other students, PhDs and so on, helped also with that postdocs. You will see. Good. Let's kick in with a slide overview of the lecture. There's going to be some introductory remarks. Then I will mainly speak about MOF catalysts, metal organic frameworks. Most of you will be familiar. We will either use them for oxidative coupling or for olefination of arenes. And then so that part on the MOF catalysis will mainly focus on activity of the catalysts, stability of the catalysts, and later on we'll switch to zeolite chemistry, and we will see how there are many similarities between what MOFs and zeolites do in this palladium catalysis, but the zeolites somehow seem also capable of conferring shape selectivity to these reactions, which is of course a very desired characteristic. And there will be some concluding remarks, quite obviously. Okay, why metal catalyzed coupling reactions indeed? Why these metal catalyzed couplings? If you look around you, you will see many consumer products, like for instance, these fragrances, but also in like sunscreen compounds, you will see compounds like cinemates. And then you see already that you have here this olefin bond on an arene installed. And also in many very common drug molecules, like for instance this molecule montelukast, which is a very widespread medicine against asthma. You also have this alkylated arene motif again. On the other hand, also biphenyls have many important applications, and one of these is in liquid crystal systems. For instance, this molecule, which has the biphenyl substituted with an alkyl and with an nitrile, is one that is actually of quite some commercial importance. And then finally also the aryl motifs, you will find them not only in many medicines like valsartan and these molecules, but also, for instance, in this molecule, which is a fungicide and which is marketed on a large scale by BASF. You see their label here, very small, and they market that as a fungicide, for instance, to be used in vineyards. Now, if you look to these molecules, of course, you have not only the alkylated arenes, so the arenes with an olefin bond installed on them, but you also have the biaryl motifs, which are present in many of these molecules and in many, many, many more. And then, of course, you would say, okay, this is a solved problem, because we have had the privilege in chemistry to have really these innovative chemists like Mr. Suzuki and Richard Heck, who have invented their respective reactions, like the Suzuki reaction between a phenyl boronic acid and then, for instance, an aryl halide, like an aryl bromide. And the Suzuki reaction will, together with the base and with palladium, with suitable ligands also in many generations, will convert that to biaryl motifs. And similarly, Heck's reaction will convert an aryl bromide together with an olefin to an alkylated arene. So you could say that's a perfect reaction. Of course, you need to do something with the bromide, and then you will produce HBr, of course, but you can solve that by adding the base like triethylamine or even many inorganic bases. They justly received the Nobel Prize for all these excellent reactions, which have in a record time actually found their way to application, of course. But there is some problems with this. First of all, there are these precursors. They are not terribly expensive, but still they do have their price in comparison with an unfunctionalized arene, of course. And there's also the aspect, of course, that if you want to install a new aryl group, for instance, at a specific place of this molecule, that you will have to do the borylation or even the bromination at a well specified position of the aromatic precursor. So in fact, even if this group, like the boronic acid or the bromine, acts as a label where the new group will be, where the new arene or the new olefin will be installed, still you have to make these compounds, these precursors, in a regioselective, in a positionally selective way. That's one disadvantage of these reactions, obviously. The other one being, of course, that you make waste, that you make sodium bromide, that you make, for instance, this organic salt of HBr, which is not that much of a problem by itself. If, for instance, and that's also done in some cases, if you can recycle this bromide salt within the factory, but still on a larger scale and in a broader perspective, it's just not an attractive property of these reactions that they do make waste. For quite some time, there has been an interest and there has been the question, can't we do this in what essentially could be considered a dehydrogenative way? So if you, for instance, want to make a biaryl motif, why don't you take just two arenes with a CH bond? And why don't you take away these hydrogen atoms to put it in a very simplified way? And as Shannon just a few minutes ago showed, in fact, this is thermodynamically even not the most difficult reaction. But of course, to make it go very well, you will still desire to drive it by an oxidant, like for instance, O2. Why not? Yeah. Same actually for the alkylation. As such, an oxidative alkylation would then be termed a Fujiwara reaction, after Mr. Fujiwara, who discovered this actually many decades ago already, with initially even stoichiometric palladium. Later this was made catalytic, and this works quite fine, or at least let's say there is a few hundred of turnovers that you can easily achieve. So at least from the viewpoint of the precursors, this is attractive because you start from cheap molecules now in this case. And also the advantage, of course, is that, for instance, if you do it with oxygen, then your waste product, your byproduct is just water. Even if you would use an oxidant like TBHP, your byproduct will just be tertiary-butanol, which is still quite acceptable in comparison with, let's say, inorganic waste, inorganic halogenated waste. But of course, there will also be some issues with these reactions. We will see that actually it's not always obvious to reach high activities, that the selectivity can be problematic, and so on and so on. Now, if we look to the challenges indeed in these oxidative CH activation reactions, what are the challenges? First of all, there's a challenge of activity. Why? Well, because in comparison with, for instance, the activation of a CBr bond, of a C-halogen bond, which is then typically done by oxidative addition on the palladium 0, here you will have to activate the arene CH bond. And that's mostly, it's the more difficult step of the whole reaction sequence. You could imagine, and initially it has been proposed that this would be an electrophilic reaction of a highly electrophilic palladium attacking an arene, but now there is, let's say, a more general vision that in many cases you can better explain this as a concerted metallation deprotonation. Metallation meaning that the arene will make a bond with the palladium, but simultaneously you will take away this proton, so it's a deprotonation, and often it's going to be a ligand on the palladium which is going to pick up this proton. This is a concerted process, so you can the correct name is indeed a concerted metallation deprotonation. That means also, if that is indeed one of the more critical and more of the difficult steps in the whole sequence, that you could make a lot of progress, that you can make these reactions work much better probably, and that has been a very thriving activity in the field of homogeneous catalysis. If you add if you add a suitable ligand to the palladium, and just a very non-exhaustive list of ligand is shown here. And for instance, you will see this ligand, which is one of the very famous ones, which is the hydroxypyridine type of ligand. But also more recently, Caro and Fernandez Ibanez in Amsterdam, they have been using these thioether ligands, and these thioethers often in combination with a carboxylic acid, then still they seem to have particularly favorable effects on the CH activation. For instance, if you want to go for an overall alkylation, these ligands support the activity quite well. Okay, so activity is a challenge and has been addressed by many ways. Another challenge which is really tricky and very difficult is selectivity. Indeed, if you have, for instance, a monosubstituted arene as is shown here, then the question is always, yeah, which of the CH bond is going to be attacked? Is it going to be the ortho CH bond, which is relatively easy to activate, as we will see later on, or maybe the meta, or maybe even the para? And in many cases, for instance, it would be highly desirable to selectively activate the para CH bond, but at least in homogeneous catalysis, that goal is rather elusive or requires very complex approaches. So there has been, for instance, Ritter's recent approach with the thioanthranylation intermediates that he makes, but in fact, it's a very involved approach if you think about it. Activity and selectivity are challenges. Stability of the catalyst is actually also quite a challenge. And stability then mainly in the sense that you want to maintain the activity, the initial activity, over long periods of time. In a very simplified way, you could say always that there is an organic and an inorganic part to this cycle, a bit like in the Walker chemistry that we all know from the textbooks. In what sense? Well, essentially, for instance, the formation of a biaryl can be considered as a dehydrogenative reaction, meaning that you oxidize the two arenes to form a biaryl molecule, but that also means that the electrons are left to the palladium which in this act is then reduced from palladium 2 to palladium 0 in the quite simplified version. Of course, in the palladium 0 state, the palladium will be very susceptible to make palladium aggregates, and reoxidizing palladium from an aggregate to palladium 2 is going to be very difficult. And in fact, if you have too much palladium aggregation, that comes down to a catalyst deactivation. Now, what we wanted to do, or let's say the main thought underlying my little talk today, is that maybe heterogenizing this palladium, that designing the appropriate solid palladium catalysts can help you in all these aspects, can make the palladium activity more stable, can even increase the initial activity of the palladium if on the solid, the palladium is surrounded by the right ligands, or that maybe the solid environment can even enhance the selectivity of this process. And that's going to be a bit the line through my talk today. Okay. So we want to go from homogeneous to heterogeneous catalysis. Obviously, a heterogeneous catalyst with often pellets that you shape the heterogeneous catalyst into is going to be much easier to retrieve from the reaction mixture than just a homogeneous complex, for instance, like palladium acetate or any other homogeneous complex with dimensions that are 1 nanometer or even less. If you speak about the granule, about the pellet that you have in heterogeneous catalysis, this is going to be, of course, much larger, and this will be easy to filter. The advantages, at least in principle, of heterogeneous catalysis are well known. You could easily separate the catalyst from the reaction mixture. You could recycle the precious metal more easily, recycle the catalyst, which is not always desired in pharmacy, but still in many other reactions, it could be desirable to recycle the catalyst, or you could reach a higher stability in some cases. And actually, we will see quite a few examples where we did reach indeed a superior stability in comparison with the heterogeneous catalyst. But there are also some disadvantages that are classically associated with the heterogeneous catalysis. For instance, that the active sites would be less defined to start here at the bottom. And yeah, that's of course quite well known, and that often you have many different types of sites, which could also result in different activity and especially selectivity, and that's pretty undesired. Sometimes it seems also that of the many heterogeneous catalysts that you would see in literature, that many of these would seem just simply too exotic to ever be brought to application. And for instance, if you think about the MOF field, I've been in this field for quite some years, and then sometimes when I see these new MOFs, I think, well, this is just too complex ever to be of any practical relevance. So this is a challenge also to strike the good balance between what is industrially feasible, what is upscalable eventually, and what is indeed innovative and new, and what does present a better performance. And then, of course, there is the idea that heterogeneous catalysts are often sensitive to deactivation, that they might have a lower activity than a homogeneous complex to which there is just free access in the solution. So all these challenges are there to be solved, and I think that we did make quite some steps towards solutions for these problems. We'll speak about several types of heterogeneous catalysts. In the first part of the talk, I will mainly speak about metal organic frameworks, and I will also mention a couple of things about the metal oxide bisphosphonates that we have also been using, although I will not be discussing these in detail. MOFs will be familiar to many of you. Essentially, a MOF can be thought of always as an infinite repetition of inorganic motifs and organic linkers, organic connectors between these inorganic motifs. For instance, one of the most famous ones that are very popular and that we have worked also a lot with are the MOFs based on zirconium clusters, like this very well-known hexanuclear zirconium cluster. And if you have many of these clusters, you can connect them with a linker that can be like a biaryl molecule, or it can be simply terephthalic acid even, and you can connect these clusters then in several dimensions, in all types of dimensions, and you can make these lattices which are very well defined, which have uniform sides to which you could then dock, for instance, a palladium. So with this type of MOFs, actually, you can consider that in many cases the building blocks are pretty cheap. The material is well defined, can be easily tuned also regarding pore size. The synthesis is scalable, as I will show. Not all these MOFs are stable enough. Some are, but many are not. So you have to be careful about that. We have also, with quite some success, been exploring the use of metal oxides, which are linked together by phosphonate type molecules. I will not discuss this in detail. You can read about this and also how we designed palladium catalysts based on these metal oxide bisphosphonates for CH activation. You can read about this in Niels's paper that is mentioned here at the bottom. An advantage of using this phosphonate oxide type of architecture is that these materials are very stable, but we have also experienced that the building blocks, like for instance this type of phosphonate already, that these building blocks are much more expensive than what you would use in a regular MOF synthesis. So I'm not going to speak about this type of material, I'm just going to speak about MOFs mainly in this first part of the talk. Okay. And let's then come to a reaction that has also been for a long time been in my dear colleague Shannon's attention, which is this coupling of arenes. Arenes like, for instance, orthoxylene. First of all, why would you want to do a homocoupling of an arene like orthoxylene? And at least much of the original attention was motivated by this polymer, by this polyimide that Yubi in Japan is producing and is making. And actually, if they make it, they need this type of bisphthalic anhydride type of molecule that they produce via quite a detour. If you look at how they do this, they actually will first oxidize the orthoxylene to phthalic anhydride and convert that to the double ester. That double ester can actually, with homogeneous catalysis, be coupled to this biaryl molecule, which then needs to be deprotected again and so on, and be converted to the double anhydride. And then you can think about making your polyimide. And of course, for a long time, it was known, and the idea was around that you could maybe do this in a much more direct way if you had a way of selectively coupling this orthoxylene to this bis-xylyl molecule, preferably this isomer of the bis-xylyl. Now, the problem was that this catalysis was not working so very well. And actually, there has been quite a lot of attention and quite a lot of excellent work also by Shannon. Actually, you were in already in the presentation, Shannon, yesterday and the day before. It has been shown that by choosing the right combination of palladium and copper, and then by also using some very specific ligands like this fluoropyridine and working with even trifluoroacetic acid, which is maybe not the most desired molecule, but still that you can achieve quite good selectivities for this desired isomer of the bis-xylyl, and that also the turnover number is quite significant. Now, this is still a di-substituted molecule, and you can imagine that it is much more easy to reach, for instance, a higher selectivity with this di-substituted molecule than it would be, for instance, with simply toluene. But anyway, the challenge already is to reach a sufficient activity also with this type of coupling reaction. Even notwithstanding the selectivity, activity is already quite important, and also even recovering the palladium is also a challenge that you really want and that we really need to meet. You heard also in the previous talk how already copper, which is much less expensive, how even recycling and recovering the copper can be a challenge. Well, with palladium, same story, of course, you do want to get your palladium out in an efficient way. So we set out on this exploration of the use of MOFs as a support for palladium in this type of coupling reactions with this type of reaction. So we wanted to couple indeed orthoxylene into the bis-xylyl, preferably this isomer, the 3,3'4'4' isomer that we wanted to make. And we compared actually a homogeneous system, and you see the conditions enumerated here. I'm not going to go into these details. We compared the homogeneous system with what we got when we added the palladium with a MOF to this system. And then remarkably, we observed that there were indeed quite some MOFs like this MOF-808, for instance, but also some other zirconium-based MOFs like this carboxylic functionalized UiO66, which all had a beneficial effect on the turnover number in these conditions here specified on the turnover number in these palladium couplings. So for instance, if the homogeneous catalyst would do something like 100 turnovers, you would go well over that if the palladium was sitting on a MOF like MOF-808. Now, what is MOF-808? You could think this is an exotic material. Well, that's actually not true. MOF-808 simply contains these hexanuclear zirconium clusters linked together by benzene tricarboxylic acid or trimesic acid, which is actually one of the simplest linkers that you could imagine in MOF chemistry. For instance, the very well-known copper BTC MOF contains also this precise linker, benzene tricarboxylic acid. And much will be to do about this position on the cluster. And so you will see that in MOF-808, actually, in principle, the cluster could be surrounded by 12 carboxylates, but only 6 of these positions are used to make the network, to build the lattice. And there are 6 carboxylates, which are actually just capping the cluster here with formic acid or with acetic acid shown on the cluster. But these are the sites that will become important in understanding and in also guiding how the palladium is sitting on this MOF material. So indeed, we saw that there was this positive, this stabilizing effect of the MOF on the activity of the palladium. And that's also shown here in this graph. Here we actually compare this for a number of temperatures. And then you see that over the whole temperature range, consistently we see superior turnover numbers when the palladium is sitting on the MOF-808 in comparison with the homogeneous case. And depending on the temperature that you consider, the effect is actually quite large. The palladium does 3 times as many turnovers as the homogeneous catalyst. The palladium on the MOF does 3 times as many turnovers as the homogeneous catalyst. And so how does this actually work? This becomes clear if you look in more detail at the kinetics. So here we plot the yield of the bi-aryls as a function of reaction time. And then you see how remarkably linear the reaction course is for the palladium on MOF-808, and to some extent also for the palladium on the UiO. And on the homogeneous catalyst, you can see indeed that there is a deactivation. And that becomes even more clear if you zoom in on the first few hours of the reaction, then you see that immediately you have this deviation from linearity for the homogeneous catalyst, whereas actually we observed that with the MOF catalyst, the blue line here, actually it's a linear curve. So essentially the MOF support impedes the deactivation of the molecular palladium catalyst. So in this whole process, apparently the deactivation, which is typically then occurring at the stage where the palladium 0 is not efficiently reoxidized, it seems that the dispersion of the palladium over the MOF makes the reoxidation eventually easier so that you have less deactivation. We spent quite some time, and I'm not going to go into all the details, but we spent quite some time in understanding how actually the MOF is doing that. And indeed, this seems to be a case where just the cluster of the MOF stabilizes the palladium and binds the palladium. Let's look in a bit detail. I hope you can see all this. This is again this cluster of MOF-808, and I think you see each time these carboxylates that are normally capping, that are surrounding the MOF-808 cluster. Now, if you apply the appropriate pretreatments like solvent washings and whatever, you can remove these carboxylates, and you will then replace the negative charge of the acetate ligand by a negative charge of a hydroxyl group and water. And actually, this is quite a reactive surface. This now acts as a reactive surface very much in the same way as you would have on some oxide materials. And that reactive surface is then going to react, these hydroxyl groups and water molecules react with palladium acetate. And eventually we get something shown like here, where the palladium is actually sitting on two of these hydroxyl groups of the MOF zirconium cluster. In fact, if you think about it, the cluster just takes over the role of a ligand with a -1 negative charge, just like the other remaining acetate on the palladium, meaning that the palladium is really monoatomically dispersed all over the clusters of this MOF material. And actually, Niels took all the effort to document that process also with vibrational spectroscopy. So there is the mu hydroxyls on the MOF-808, but especially here you can also see these other hydroxyl groups, which are shown here. You can also see in the infrared spectrum. And then if the material, so the hydroxyl containing MOF-808 reacts with the palladium acetate, you see the disappearance of these hydroxyl groups. And that's proof for an anchoring of the palladium on these clusters. And the precise binding mode of palladium on the cluster, we actually also documented in more detail by XFs, by XAS measurements. And then the overall picture that emerges from that, without going into all these spectroscopy details, is that indeed the palladium is sitting one by one on this zirconium cluster of the MOF. And that's how the MOF stabilizes the palladium's activity eventually. Okay, so you see that even just palladium on a MOF, on just the pure MOF without any other modification, is already giving some important advantages, stabilizes the palladium in its oxidation catalysis activity. As I told you already, there is another way of even further promoting the activity and further fostering the activity of this palladium, and that is to work on the ligands in more detail. And these ligands with these thioethers, especially like proposed by Fernando Ibanez, by Caro, they inspired us to also work to modify them off and to really design a hybrid single-site catalyst by replacing these thioether carboxylic acid ligands by a ligand that we then devised, and which is actually quite simple to make, which is this tetrahydrothiophene with 2 carboxylic acid groups. Now, the concept that we did is we thought, well, we can actually also use this MOF-808 structure as kind of a scaffold to anchor this type of thioether carboxylic acid ligand. And that's precisely what we did. So if indeed we zoom in again on this MOF-808 structure, we worked with this cluster and we replaced these acetic acid or these acetate linkers. We replaced this with this ligand, which we just termed L1. So actually one of the carboxylic acid groups is now just being docked on the zirconium cluster, while you still have the thioether and also a carboxylic acid free to coordinate the palladium. And that's precisely what we did. So we actually used now the MOF not as much as a support itself, but as a platform to dock ligands upon to. Yeah? And then you get this type of situation with the palladium and now docked on the thioether carboxylic acid, which is itself attached to the MOF surface. Yeah? You can give many types of physical-chemical proof that this is indeed what happens if you do this type of modification of material like MOF-808, but just one to show you, which is then like the real physical proof, that's a porosity measurement. And actually MOF-808 has very large pores, and the porosity for us in heterogeneous catalysis and interested in and researchers interested in porous materials, you would measure that always with nitrogen phase dissorption. And actually the MOF-808 as such has very large pores with a pore width typically, if you measure it in with a nitrogen phase dissorption of 2 nanometer diameter. Now, if you dock the ligand 1 at this thioether carboxylic acid molecule to MOF-808, then you see that you really have a decrease of the pore size, of the average pore size, which is a good proof that actually this ligand is spread all over the MOF in a rather homogeneous way. We did also many other characterizations, like for instance solid state NMR, and that also proves that this ligand is actually in a very homogeneous fashion distributed all over the lattice of this MOF-808 material. We also looked actually at the palladium siting itself, again with XAS, And of course, that's a very nice case to look at with XAS because you have all these different binding atoms, the sulfur and the oxygen, and that gives you a very clear fingerprint. So we can indeed prove from these XAS data that the palladium is coordinating both to the carboxylic acid, but also to the thioether of the tetrahydrothiophene ring in the ligand. And that there is also still an acetate ligand, that's the other ligand that's in the resting state still available on the palladium if you do the loading of this MOF material with palladium acetate. We can also exclude, for instance, that there would be palladium 0 clusters because the typical binding distances that you would have in a palladium foil, they are just not there when you have the palladium 2 loaded on this ligand modified MOF 808. Okay. And then to the catalysis, actually in this case, we decided not to use oxygen, and I will detail the reasons immediately. And we wanted to use now this material for doing alkynylations. And the model reaction that we selected was actually this Arene, and we wanted to alkynylate that with butyl acrylate, and then you would of course make this cinnamate type of molecule. And I'm not going to discuss all the catalytic optimizations that we did for this reaction, or that Niels did for this reaction, but maybe the most telling about the effect of the MOF, in this case of the ligand 1 modified MOF, so the MOF modified with this thioether ligand, is what you see here in the initial kinetics. If you compare the homogeneous reaction with palladium acetate with the reaction with just palladium on the MOF 808, so without the thioether. And if you see then what happens with the thioether ligand, and then it's obvious, of course, that the initial rate from the onset of the reaction is just higher if you modify the MOF with this thioether carboxylic acid group. And that's why this is the best catalyst in this reaction, actually. As an oxidant, we actually used tertiary-butyl peroxybenzoate, which is kind of a special oxidant, but this is an oxidant that really works really well in this reaction. Actually, this was also partially motivated by the fact that we did in an EU project together with Janssen, with Johnson & Johnson, and they really did not want to work with oxygen. And to come back to the theme that we touched upon in the previous lecture, they really did not at all want to work with oxygen. So actually we were happy and lucky that this oxidant that we identified, and which is also a very safe one to work actually, so it's a per ester if you want, it's tertiary-butyl peroxybenzoate, that this gives good rates and good activity with the palladium in this case. We did a whole substrate scope with this system. So actually you can use it in a very flexible way for doing all these alkynylations. And then you will see that with these methoxy substituted arenes, but also with, for instance, the furans and so on, we got to high yields in many cases. The selectivity is one, of course, that could be improved because here we are in a system, this MOF 808 has very large pores. So there is not really a way that there's not really a way yet that by the porosity you could influence upon the positional selectivity of the alkynylation in this case. We also took that to larger scale. For instance, these are a couple of the molecules which you see here that Niels also made at larger scale, at gram scale, synthesis-wise. And for instance, these two molecules, these are, of course, UV absorbers. So you would find them, amyloxate and octinoxate, you would find them in sunscreens. And this molecule, which again has this cinnamate motif, resinamine is actually a drug molecule that you would take if you have hypertension problems, if your blood pressure is too high. Of course, you could say that such a MOF system is too exotic, and you could wonder, is this then really a molecule, is this really a catalyst that you could scale? And I'm not going to go too deeply into this, but actually part of this work was also performed in the frame of this EU project that we coordinated, HCCAT. And one of the ideas was essentially that such alkynylations, like you find, for instance, in this molecule, which is rilpivirine, that's an anti-HIV medicine, that these alkynylations are really also of industrial relevance. And that's why also a company like J&J, Janssen, was interested in looking at these alkynylations. I'm not going to give the full account of this, but what I really wanted to show to you is that even if you think that this is an exotic catalyst, we actually were successful in doing this at pilot scale. Why? Because all the compounds that we use, the MOF, but also, for instance, this linker molecule, this ligand that we functionalize the MOF with, they're actually easy, cheap, and easy to synthesize at large scale also. For instance, if you think about this tetrahydrothiophene, it's actually very easy to synthesize it, starting just from 2,5-dibromo adipic acid. So if you just have adipic acid with bromine substituents on positions 2 and 5, it's very easy to convert that to this tetrahydrothiophene, which can then be directly used. Same story a bit for the MOF. The MOF, you could think this is exotic, but actually no. The zirconium MOF with benzene tricarboxylic acid was made by our colleagues, by Karl Petter Liderud in Norway, with Prof MOF, which is a small company specializing in these MOF syntheses. They made it at a sufficient scale, which meant that we had a lot of this MOF powder that we could functionalize with the ligand, which was then actually shaped into pellets eventually. And so together with partners like Axel One in France, but also the Fraunhofer Institute, they eventually made, and I hope you can see that, they made this into pellets of the MOF that we then loaded with palladium. And so here you see a couple of these pellets. We loaded them with palladium, and we took in this project the chemistry all the way to the upscaling actually here in the plant at Janssen, where they were able to reproduce the results that we had actually at the small scale, where they could do also high conversions with these alkylation reactions. Okay, so now let's go to a different part of the lecture. We have shown already that MOFs can have beneficial effects regarding stability, regarding activity on a palladium catalyzed reaction, but there is one still elephant in the room, and that's of course the selectivity, the site selectivity of CH activation reactions. And already many years ago, actually, Murray, for instance, and also Hans de Vries and Piet van Leeuwen, they did seminal work in the sense that they showed that if you have a directing group, that then the CH bond in ortho is quite easy to selectively activate. And many other researchers, like also Melanie Sanford in her early days, have worked on the same theme. So that's not a challenge anymore. You can do it with palladium, you can do it with ruthenium, like Lutz Ackermann has done many times. So that's easy. It gets much more complicated if you want to go to the meta position, quite obviously. And then you need to go to these much more elaborate catalyst design with auxiliaries and then groups that you have to remove and so on and so on. So meta is already much more difficult and it's not easily done at large scale. Para is then the really difficult one. And there is, for instance, the approach by Tobias Ritter. But in fact, if you look at that from the viewpoint of atom economy, it's just not something that you would want to do, to work with all these thioanthranil auxiliaries. So we wanted to do something about that, and that's where the zeolites come in. And zeolites is, of course, a bit an unlikely combination, if you think about it, if you read the whole homogeneous literature, like all of you undoubtedly do. Zeolites is probably a field which is less familiar to you, and normally zeolites are associated with solid catalysis, heterogeneous catalysis in Dresde conditions, proton acidic catalysis also. But of course, in that field, they have quite a reputation. They have been used for many decades. Why? Because in a zeolite, you can change the number of proton sites that you have by varying typically the silicon to aluminum ratio. A zeolite is essentially SiO2, in which you replace part of the silicon by aluminum. So each time you replace a silicon by an aluminum, you get a -1 negative charge in the lattice, which means that there can be, for instance, a proton sitting here. But actually, this can also serve as charge compensation to a catalytic cation, like, for instance, palladium. Why not? Another positive aspect of zeolites is that they are very stable. They have very well defined and tunable pore sizes, and there is like 100 or 200 different zeolite topologies known till now. So we had the idea that maybe it could be interesting to use zeolites in these palladium catalyzed reactions. And I'm not going to tell the whole story, but indeed we started to look at Arene coupling reactions, for instance, coupling of two toluenes to make bitolulyl in the presence of zeolites. And initially we had envisioned that these zeolites could replace the strong acid co-catalysts, like for instance paratoluene sulfonic acid, that are often used in these reactions. So that was a bit the outset of our reactions and of our research. We thought, well, let's just use a solid acid instead of the homogeneous acid. It's always going to simplify the workup, but actually it turned out that there were quite some other effects going on. The idea that we have about the active site in all these reactions, and that's just to make life easier for you, and we have a lot of evidence for that, and I will show some of that evidence. But the idea that we have is that basically what is active in these reactions is a palladium, which is originating from palladium acetate. But in fact, the palladium acetate, which is trimeric but could be monomeric and so on, reacts with an acid proton in the zeolite. The result is that one of these acetate ligands is protonated again, so it leaves the zeolite. The palladium is then sitting on the zeolite with one acetate ligand still on the palladium, and the other charge for the palladium too is actually compensated by the lattice. That's a bit the basic idea of how we think the active site could often look in these materials. But then, of course, you can start varying the zeolite types, and there are so many zeolites that we tested and that you could think of. The phosphosite type zeolite Y, typically. This you can just take as the model for a very spacious zeolite with very large cages. The super cages are larger than a nanometer, large windows also. Of course, you can go to very small porous zeolites like you would have in the Denox catalysts, but that's of course useless because then even the reactants like toluene or like xylene could no longer enter the pores. But for instance, zeolite beta could strike an interesting compromise because the pore sizes are still large enough to still allow the diffusion in and out of the reactants and even products like a bitolil, but still the pores are quite more constrained than what you would have with a phosphosite zeolite. And these are just some of the results that we obtained. We have looked a lot, Yannick has looked a lot at these reactions of toluene. And then you can make bitolil. Why would you want to make bitolil first and for all? Well, because there is many molecules like these, for instance, these bis, like these phthalate analogs of like these bisphenol analogs that you could make from the bitolil. So in fact, to the extent that the industry wants to get rid of the bisphenols and all that molecules, these biaryl motifs are enjoying a lot of attention nowadays because they don't have many of the adverse effects that, for instance, the bisphenols would have. Now let's look at the reaction data. And in many of these data we have, in many of these plots, we have the turnover number. So the number of moles of arene that we convert per mole of palladium at the left side. And then the product distribution is shown on the other axis. So the diamonds typically that you have, the black diamonds are the activity. And then we see that indeed, for instance, the palladium in combination with paratoluene sulfonic acid gives quite some good turnover numbers. But what you essentially make is a mix of all possible isomers. And the isomers are labeled here in all these colors. Of course, if you couple two toluenes, and if you do that in a totally indiscriminate way, you can make 6 isomers, orthopara units. You see them all. And of course, it would be desirable to make at least one or several of these selectively. If you look at what, for instance, zeolite Y does with an adapted silicon to aluminum ratio, then you would see that actually zeolite Y does fine regarding activity, but you still make pretty indiscriminately, and actually even with some ortho preference, you make many isomers. But then we were very surprised and also pleased to see that indeed zeolite beta, that in zeolite beta, you start to have very strong deviations from the statistical product distribution. And for instance, you make a lot of the para-para isomer. And that's, of course, quite a surprise. And you wouldn't think how this is possible because these concepts of palladium molecular catalysis had before never been implemented in a zeolite, but somehow the palladium beta catalyst makes a lot of this para-para isomer. To just convince you that these effects are pretty drastic and surprising, here is even a very early chromatogram from many years ago in which we compare the product distribution of zeolite Y with that of zeolite beta. And then you see that indeed there is this very big peak of the para-para product that stands out with zeolite beta, whereas on zeolite Y and also in homogeneous catalysis, you would have a much more statistical distribution. Same idea comes out of the proton NMR that you see here. This is just a crude proton NMR of a reaction mixture. And then you see that even in the crude mixture, already the spectrum in this aromatic domain is dominated by actually para-disubstituted arenes. So each of these rings is now para-disubstituted, and that gives you this typical pattern that all of you know very well from your basic organic identification classes. We have worked a lot on this system, on this palladium beta, and actually the best performance is obtained if together with the acetate, which is still in the zeolite because of the origin of the palladium precursor, because of the palladium acetate, if you add some extra acetic acid, and then you really can get to very high turnover numbers, for instance, 400 molecules of toluene that you convert per molecule per palladium center, and that's even much higher than what you get with the homogeneous best system, and then you of course get the shape selectivity on top of that, because you see that now indeed the para-para isomer is is produced in like 70–80% selectivity in pretty high selectivities, which is quite special if you consider that you could make the 6 isomers actually. Toluene is not the only case in which we have such selectivities. This just some other data to show that this selectivity is pretty general. For instance, if you would couple benzene, then of course the main product is biphenyl, and there is no positional selectivity in biphenyl. But you could go on to produce some terphenyl, and then you see, for instance, that in this reaction with the beta-zeolite, within the terphenyl fraction, which is not too much, but within the terphenyl fraction, again, the para product is the dominant one. So that's the blue bar here. So you see that also in this production of compounds like terphenyl, you get a very considerable shape selectivity. And that also holds for instance, anisole. In the case of anisole, we get again to a very high selectivity for the para-para product of 4,4, which is the light blue bar here. If you compare, for instance, what happens with paratoluene sulfonic acid, then we see that actually with the paratoluene sulfonic acid, we got a byproduct, bis-anisyl. If we try to couple anisole to bi-anisyl, then we get the bis-anisyl F, which means that actually the methoxy group is decomposed and starts to bridge with a methylene bridge between 2 of these arene moieties, which is not what we desire. So indeed, again, the beta catalyst as a quite superior catalyst. Same story actually with the palladium beta and orthoxylene. So that was a bit the starting point of all this, because that's a reaction that also works rather well or very well with the homogeneous catalyst. But you see that again, in comparison with, for instance, a Y-zeolite or the paratoluene sulfonic acid, even without any special ligand like the fluoropyridine, you get to a very high positional selectivity for this desired 3', 4' isomer of the orthoxylene, coupled with, again, high turnovers for this palladium beta catalyst. An important question is, of course, is this truly heterogeneous catalysis? That's something that you always want to consider. Actually, this is a filtration test. I hope you can see it, but actually at this point where my little red cursor is now, we did the splitting, and then in the splitting, you see that we have progress of the reaction, but no further progress when you look just at the filtrate. So indeed, this is heterogeneous catalysis. We have also looked a lot at how much of the zeolite you need in comparison to the palladium. And then somehow the activity of the palladium increases up to the point where you have precisely 1 aluminum per palladium in the whole system, which means that one of the charges of the palladium is indeed compensated by the zeolite framework. We looked also at the active site, and for instance, with EXAFs, we got considerable proof also for such a siting in which the palladium is sitting on the on one hand on the zeolite, with here 1 aluminum. On the other hand, when there is still 1 acetate in the neighborhood of the palladium. We have also quite some solid state NMR evidence that I'm not going to discuss, but the idea is just 1 acetate sitting on an isolated palladium. We looked a lot at the kinetics also to understand the system better. And of course, you hope also from the kinetics to deduce some information regarding the mechanism. First of all, because you are in a porous material, you need to ascertain that indeed you would be in chemical and not in diffusional control. And then you can make these plots of the ln of the rate versus the reciprocal temperature. And then it seems that as long as the temperature is low enough, that indeed you are in chemical control with a pretty high apparent activation energy. Yeah. And then, of course, you can start to wonder, can we deduce also something from these kinetics regarding the mechanism? It's always very tempting to say, of course, that such an arene coupling, that this would be a bimetallic mechanism, which is in very simplified form shown here, meaning that actually each of the arene partners would be activated on a separated palladium. And then you would expect that you need a transmetallation, transferring 1 aryl group from 1 palladium to another to make this bis-aryl palladium intermediate, which would then do a reductive elimination and produce the bis-arene. And then you could expect a second order in palladium, but that's not what we saw. We saw actually that there was definitely a first order in palladium, which hints to us that it's likely that the 2 arenes are activated sequentially on the same palladium atom. This is the mechanism that actually, with the help of our theoretical colleagues in Ghent University, Veronique van Spijbroek and her group, we eventually propose. One of the basic ideas of one of the things we think is that the 2 arenes are indeed activated in 2 different steps. Because in the first in the activation of the first arene, there is still this acetate which can assist the palladium in activating the toluene in a concerted methylation deprotonation. So the first step is indeed such a CMD step in which actually the acetate as a base will pick up a proton from the toluene. And then the second step, of course, is that's one which is more hypothetical actually, but most computational evidence in fact goes to an attack by this first tolil ligand on the palladium on a second toluene molecule in kind of a migratory insertion, so that eventually you do have a bis aryl compound which is made and which is then leaving the catalyst, leaving the zeolite pores. Finally, we still need to reoxidize the palladium. I would consider this is not too difficult. We don't have evidence. If you do 400 turnovers, there is not too much evidence that the reoxidation of the palladium, maybe a hydride, is problematic, but we assume that this is actually quite a fast step. This still leaves us with the question, why do we have this positional selectivity? Well, it seems that at least this first step, that there is a, so when the CMD with the palladium coordinated on the zeolite, but also by the acetate, as you see here, that at least this first step favors heavily the para-activation. So it seems that the constrained environment, the sterilely constrained environment in the zeolite pores really favors this first para-activation of the toluene. In the second step, actually, where we have this migratory insertion, probably we are less sure why there is still quite a high selectivity, but overall the result remains, of course, that we have a very selective formation of 1 out of the 6 potential isomers of, for instance, bitolil. The next challenge then, and I'm just almost at the end because I see that we are nearing 6 o'clock. The next challenge, of course, is then, could you go beyond simply homocoupling of benzene or of toluene or of anisole or of whatever, xylene? Could you also go to heterocouplings? And there, of course, from an organic chemical point of view, it becomes quite difficult, but because there you really would need a kind of a different, let's say, an orthogonal reactivity of the 2 arenes that you would involve. And to some extent, we have been already quite successful in getting out also in shaping this system up to a system that can successfully do heterocouplings also, for instance, of benzofuran and toluene. And that's a case which so far really works really quite nicely, in which we see all these concepts of not only shape selectivity, but then also selective formation of the heterocoupled product come back. We need to modify the system. For instance, now we Yannick adds pivalic acid actually as an additive rather than acetic acid. And of course, if you just throw together toluene and benzofuran, you can count it, but actually you can make 12 isomers. So you can make 3 of these coupled benzofurans, and you can make the 6 bitolils, and then you can also make 3 different heterocoupled products. Now, with all the optimizations and all the modifications to the system that Yannick did, not only he was able to increase the yields. As you see here, the yields are getting higher and higher. We are not at 100%, but still we are at pretty high yields based on the benzofuran. But also you see that we have a significant control over the selectivity, because in brown here in the graph, we show the bibenzofurans, and they are negligible. In gray, we show the bitolils. They are also negligible. They are just below 10%. So that means already that the selectivity for the for let's say the tolylated benzofurans is 85%. And within that fraction, we again have a strong preference for the para tolil product that we make. So even in this challenging CH-CH coupling of 2 different molecules, we are capable of getting to high yields and high selectivities, again, in this zeolite beta environment, now appropriately adapted. Yeah? And this holds not only for this coupling of benzofuran with toluene, but also the reaction of benzofuran and benzene already is quite successful. We see that again, we make a lot of the heterocoupled product, which is this 2-phenylbenzofuran, which is here in darker blue, and also with the coupling of anisole and benzofuran, we have made quite some, we have seen some quite interesting results with the beta pivalic acid system. Which brings me a bit, it's more or less 6 o'clock, to my conclusion, namely that I hope that I have been able to convince you that with several heterogenized palladium systems, either on a MOF, as shown here, or in a zeolite, We can do something about the stability, the recyclability of the catalysts. We have scalable catalysts because, for instance, the palladium on zeolite beta, the zeolite beta is just, it's a commodity. It's a material which is used on huge scale in petrochemistry. So yeah, that's really not a problem to do that at large scale. The palladium is still the most expensive one, but then of course, if we go to higher and higher turnover numbers, all the better. And even in some cases, we have already been quite successful in making these systems selective for a desired CH bond. And we are working further on that, of course. Okay, then some people that I really want to thank. Most of all, of course, my co-authors, Niels and Yannick, for all their excellent work over the years, their visionary work. Many of the students have helped with that, but I certainly want to mention Sam and Jesse, who as master students have worked also a lot in these topics, and they're now pursuing their own interests also and their own PhD in our group, and all our sponsors like the Flanders Science Foundation, the EU, and so on. And I'm very, very grateful that many of you stayed till the end to listen to me. Thanks for that. Okay, Shavik, up to you.
Yeah, Dirk, thank you very much for very inspiring chemistry with a heterogeneous catalyst, microporous catalyst, and we learned a lot, definitely. Like we jumped from homogeneous to heterogeneous systems. I'll come back to the real point later. Please keep in mind, normally in our this lecture series, we try to give one common questions to our speaker, scientific question, and then we just like to hear your opinion. But that I will come later. So I would like to hear first from you as well as Shannon, a common topic. But of course, I have plenty of questions. My first question is, in your MOF system, you have shown the numbers, but I'm not, I would say, very much into that MOF chemistry. So I'd just like to know that which functional group is actually very important to have the reactivity in that system.
Well, there is different, we discussed at least two different systems, and either you can use just the inorganic clusters as a way of, as a well-defined oxide in a way. And so in fact, you have something which is similar to an oxide surface. Either you can use the inorganic clusters, or you can really use also the MOFs as a platform to dock your ligands upon. And then in the second system, we were working rather with the thioether carboxylic acid ligand, actually. So you can use it in many ways.
Okay, but how does it affect the selectivity in your system?
Well, the selectivity, there is in the MOFs, usually we have been working with very spacious MOFs. I mean, there's a lot of space. Yeah, and there actually the selectivity is most of the time not essentially different from what you would have with a homogeneous catalyst. So that's more unique to the zeolites, for sure.
I agree with you that the orthoselectivity, orthostage activation is, at this moment, is not so attractive. Meta is challenging. Template methods you have mentioned. There are two other methods as well, like radical method. Mike Greene is doing fantastic chemistry. Then there is one traceless carbon dioxide method. For say you use CO2, carboxylic acid. It's kind of cheating, but it's a nice approach. Yeah. And I agree completely with you that para CH1 activation is in that way, the distal CH1 activation can be quite challenging. And in that case, actually, you explained the mechanism, which was very clear. What I wanted to know is why only zeolite is giving that paraselectivity, because one point that you mentioned, that it's kind of let's say very compact system, so it kind of stopped the rotation. The rotational force is kind of stopped. If this is the reason, then can it be done also with other materials?
Yeah, it's a good question. I think one of the points is that the palladium is tightly coordinated on the zeolite wall. And it's going to be very hard to identify another porous system in which you will have a similar coordination. Yeah, that's my vision on it. Knowing the whole world of porous materials, I don't see immediately another class of materials or another type of material in which you would have something similar. Yeah.
I guess it's still a lot of mechanistic things are going on, I'm pretty sure, in your lab. So maybe soon you'll have much more clear answer that what is exactly happening for the paraselectivity. Because I know it's a kind of still a black box. I mean, we try to say many reasons, both from the homogeneous, heterogeneous here, but it's still kind of a black box at this moment.
Well, but maybe a naive way of telling or of discussing this could be that the palladium is really sitting against the pore wall, so that, let's say, half of the sphere around the palladium is just not accessible because there you have the zeolite. So that means that the number of ways, I mean, an ortho, I mean, if the ortho CH bond would approach the palladium, the metal group just is sitting in the way, and that's why it doesn't work. So we have also seen that in some zeolites where the palladium sighting is a bit different, we don't have the shape selective effect. So I think that in some zeolites, just the coordination of the palladium is fundamentally different. And that's something which is known also in zeolite chemistry, that there are different coordination modes of metal cations depending on even the geometry of the zeolites. Beta-zeolites has 6 rings, has 5 rings. We don't know precisely where the palladium is sitting. But for instance, in the phosphosite, where the cation sightings are very different, we don't have a shape selective effect. I think just the palladium is sitting somewhere, wherever, in the middle of the cage or so, and doing its job happily there. But we don't have the same shape selectivity. We have seen that there are zeolites that are structurally similar to beta, and that tend to produce similar shape selectivities. But none of them approaches the practicality and the easy availability of the beta zeolite. You could imagine many other topologies. People really familiar or deeply into the zeolite science would say, oh, but this and that topology should also do it. And they're right, they're right. It also does work. But another complexity is, of course, also that you need to be sure that your palladium is only sitting at the desired place in these zeolite interiors, for instance, at the intersections in the beta zeolite framework, and not, for instance, at the outside. So you can easily ruin also such a shape selectivity by having 5 or 10% of the palladium in the wrong space, in the wrong place. And then just, you know, the catalysis could go on in a shape selective way inside the zeolite, but also in a non-shape selective way outside the zeolite, and that would ruin your selectivity. And I guess that's also happening in quite some materials or in quite some catalysts that we even have produced ourselves. So it's not so simple.
I understand. Yeah, I think Robert has a question. Robert, please go ahead.
Yeah, so thank you, Dirk, also from my side for the very interesting talk. So my question is moving from selectivity to mass transfer. So since you dispersed the metals or the active centers in the pores, at some point pore diffusion will become or may become rate limiting. Do you have an idea about the fraction of the pores or the degree of pore utilization? And did you try to engineer your pores to improve the mass transfer?
Yeah, good question, Robert, and a very classical question from the heterogeneous catalysis side. You will have noticed, maybe I was too short on that, that we determined the apparent activation energy. It was in one of the last slides. I can try to show it again, but because it's really the thing, of course. Let me try. You see this one?
Yeah.
Yeah.
Yes.
Well, this is, of course, the classical test that, or one of the classical tests that one could do. So you vary the temperature, and of course you need to do this in the right conditions and so on. But then you indeed see that we have a pretty high activation energy, 70, 80, 90 C, pretty high. This is in heterogeneous catalysis, in catalysis with porous materials, this is considered too high for the process to be under diffusional control. Yeah? You can imagine many theories about that, but indeed, I mean, if you, for instance, if you read Mark Davis's textbook about this, 80, 90 kilojoules per mole, then you are already pretty safely into chemical control, which means actually that at that moment, all the palladiums that are active are not subject to diffusional resistance. If you go to higher temperature, we all know that a chemical reaction is more thermally stimulated than a diffusional phenomenon. And then we see this transition to a lower activation energy. Of course, at the highest temperatures, it becomes tricky to distinguish between deactivation, because maybe some slow diffusion even of the oxygen into the zeolite and so on. So, but indeed, at a sufficiently low temperature, you can be sure that there is no diffusion limitation. yeah. And of course, we do need the catalysis to go on to happen within the pores, because otherwise we would never have the shape selectivity. That's also the risk if you then go for pore engineering, and you can try to create mesopores and whatever, but then you also lose your shape selective environment. And if then you end up with palladium sitting in a meso rather than in a micropore, out goes the selectivity. So yeah, I hope that's a bit clear. What you can also do, of course, is play with the size of the crystals, and then beta, luckily, is one of the systems that typically comes in small crystals. So you have 100 nanometer crystals in an industrial beta.
Thank you.
Yeah, Dirk, we have some questions from the audience. So from Francisco de Azambuza, Professor De Vos, great talk regarding the first part where palladium is dispersed directly on MOF-808. Is it possible to modulate the palladium reactivity through modification of the MOF linker electronics or even the cluster metallic composition?
I'm sure we tried that sometimes. Niels tried it, and I'm sure he's in the talk also. But actually, Francisco is sitting in the same hallway as we are, so we could discuss that. He's in a different group. Well, the question is, of course, how will this affect the palladium at its various stages of activity? Because I didn't discuss it even, but of course, in such reactions, the palladium still needs a reoxidation. And Shannon has spoken a lot about the oxidation of the palladium and the redox potentials. Definitely, there's going to be an effect of the support on the reoxidizability of the palladium, for sure, in ways that are very difficult to predict. But there's going to be many effects. The surroundings of the palladium, of course, also determine the reactivity in the CMD. Is there some type of basic site around that can pick up a proton for doing a CMD? Or is maybe the palladium rather electrophilic? How electrophilic is the palladium still? Yeah, that it's hard to predict. I think it will also be hard to tell if you look to the overall reaction, because these are complex reactions. There happen at least 2-3 different elementary steps, types of elementary steps. Yeah, the question is also which of these steps is going to be affected most. We are empirical chemists, I admit that, but we want to make things work.
We have one very interesting question. So it's from Anonymous, but thank you very much for this very nice lecture. Since the X-ray absorption spectroscopy did not show the palladium-palladium bond signal, can we state that these palladium functionalized MOFs are single atom catalysts? Yes. That's our belief. We are a Catholic university, so we need to have some beliefs. And in my case, the belief is that it's a monoatomic catalyst. Yeah, well, let's say that we avoid the formation of palladium colloids. And that also in the related homogeneous cases, I think all the research by many teams, including Shannon, first and foremost, will show that this type of catalysis works well if you do not have clusters. Yeah, absolutely. Of course, many of us would tend to associate a palladium heterogeneous catalyst with palladium nanoparticles on a support like palladium on carbon, but that's not what we have here already in the first place, because somehow the first activation, the reaction needs to start from a palladium 2+ and not from a colloid. And that holds for the MOF, that also holds for the zeolite, quite obviously. There is one more question from Yuhu. Thank you for your nice presentation. I'm a little curious about the stability of zeolite beta catalyst. Did you observe some hydrocarbons deposition on zeolite after the reaction? That's also a good question. Actually, very little, which is important because here you are by definition in the unfavorable situation that you have a large product. I mean, you have a bitollyl, and that's not obvious because in principle, if in the zeolite catalyzed reaction, the product that you make is larger than the reactant, you would easily end up in pore clogging. So that plays against you. On the other hand, if you do 400 turnovers per palladium, you know that it's not a real problem, that the problem is only minor. But yeah, you have to be aware of that. In fact,
and that's also in the publication that Yannick wrote about it, and also in Niels's work that team came back. Maybe one of the more tricky things, or the real deactivation, comes from a somewhat unexpected side, namely that if you use oxygen as an oxidant, you make water, and water will have a high affinity for many of these porous materials. So the deactivating thing somehow is more water, which also explains why in this zeolite beta, it's better to work with a well-adjusted high silicon to aluminum ratio. So the zeolite community thrives in inventing all types of theories about silicon to aluminum ratio and what it can do for your reaction. Of course, this always has an effect because a zeolite with a high silicon content is much more hydrophobic than the one than a zeolite X, for instance, at 13X. But one of the effects here is clearly that this will just push out the water. The more hydrophobic the zeolite is, the more it will push out the water. And this is just a mechanism of preventing deactivation. Yes. Yeah. I think Shannon has also a question.
Yes. Now I see Shannon has a question. Shannon, please.
Hi, Dirk. Yeah, this is a great system you've developed. Various questions. You may have answered one of them just now related to the effect of water. Are these infinitely stable catalysts in the sense that the only thing limiting is really just the practical time limits of how long you want it to run, or do they eventually die? And do you understand anything about the lifetime? Does it relate to the water effects that you're talking about here?
The water effect is important to rationalize the difference between zeolites with different silicon to aluminum ratio, but they do deactivate, and eventually you do make palladium 0. Yannick has struggled with this for a long time on how to regenerate, and he did identify eventually procedures for redispersing the palladium 0, which is not such an unknown terrain in zeolite chemistry, in heterogeneous catalysis. If you look, for instance, to, what shall I say, platinum on some other zeolites, if you have clusters, there are known procedures for redispersing. At least platinum colloids and zeolites, they're not obvious. They're a bit special. But the fact that this is successful also has to do with the idea that zeolites are just very good multidentate ligands for such cations. So you can thermodynamically really go to a situation where from a metal colloid on a zeolite, you go to, again, highly dispersed platinum 2+. There's not too many works on this, but they exist.
What's the general, I don't know this literature, what is the general procedure for redispersion?
Oh, they would go to high temperature, but with even oxygen and oxidants. I mean, yeah, this type of thing. Yeah.
And I guess I didn't catch all the details, and I should have been paying closer attention if it was there. The solvent is usually hydrocarbon solvent, or is it? The reason I'm asking is many palladium homogeneous reactions use acetic acid or some sort of carboxylic acid additive, and those engage in very facile ligand exchange. And I'm wondering if you have a system where acetic acid is a common solvent in a homogeneous solution, if this is going to start leaching the palladium due to palladium exchange, or it. So in other words, are these favored in part by the ability to use a hydrocarbon solvent that
yes.
Essentially avoids ligand exchange?
Yeah, Yannick has a lot of experience with that. The best reactions are obtained in largely hydrocarbon, but with a significant addition of the acetic acid. So already the fact that you keep seeing these highly shape selective isomer formations proves that it's happening inside the zeolite and that you do not have leaching. And of course, that's also a pessimistic scenario that I was immediately thinking of myself. If the acetic acid would leach out the palladium out of the zeolite, you will not have any longer the shape selective effect. But yes, there are like optimal ratios to get the catalysis to very high turnover numbers, optimal ratios of acetic acid to the arene. So most of the time we work in the arene, which in my view also has the highly beneficial effect that thermodynamically, such an arene is a very good solvent to extract like the biaryls from the zeolite pores. Because of course, if you want to have a good desorption of your product, you should be sure, naively saying that your product is feeling well and at ease in the solvent. And then, of course, toluene is a very good solvent for bitoluene, for instance, and anisole is a very good solvent for bianisole. But yes, indeed, there are optimal ratios of acetic acid to palladium. You can also do the catalysis with just the 2 acetates originating from the palladium acetate with which you loaded the zeolite. So even 2 acetates per palladium will already do the job, but you will go much higher in turnover number if you provide more acetic acid. And in our view, this has also to do with the availability of sufficient acetate at the moment when, for instance, you reoxidize the palladium 0 or palladium hydride to palladium 2, because you need to get rid of your hydride, and even all these aspects are they are also very difficult to characterize. What do we precisely have as a reduced state? Let's say, do we have a palladium hydride? Do we have palladium 0? We don't know. It's very hard to characterize that in realistic conditions, but the feeling is certainly that in many steps, some extra acetic acid hovering around in the pores helps in the catalysis. We also studied the selective adsorption, or let's say the adsorption equilibria of acetic acid and the arene in the pores of the zeolite. And then you know that there is quite some acetic acid in the pores sitting around, but there is also a lot of arene. Yeah, but all in all, this does not result in acetic acid leaching out to palladium from the zeolite.
And just one quick, hopefully quick, is there a way of thinking about the pKa of that site in this pore, the OH site that you exchange for palladium? How do I compare that to, say, acetic acid pKa? Is it much more acidic? Is it?
Yes.
Yes. So it's more like a tosylate or a triplet or something of this nature.
Yeah, of course, that brings us to the whole discussion of pKa's in zeolite acidity. I would always tend to take it to the practical side and say, you know, this is the type of acidity with which in industry they would do an alkylation of isobutane with butenes, which is now a process that runs with, whatever, sulfuric acid or something like that. So the acidity of zeolite beta is in that category. It's a strong acid. It's a very strong acid.
I think that answers my question, because the essence is that the preference to put a proton there instead of palladium is not going to be very favored. So that exchange, the reason acetic acid doesn't cause problems is because the acidity is so high that there's not a great preference to put an acetate and then put a proton on the zeolite.
That's a correct way of looking at it, Shannon. Yes.
Yeah, okay.
There is one quick question. So if this is from Alemão Gasho, the question is, if electron withdrawing groups are present on aryles, which position is more favored for coupling?
Yeah, that's a good question. First of all, benzene reacts quite well. If you put, if you're really going to put electron withdrawing groups on the system, it's just going to have a much decreased activity, because the arene is not going to be sufficiently reactive anymore. And so we do have some data on that, but I can't tell you by heart, actually.
Okay. So now both Dirk and Shannon, thank you very much for your lecture discussion. Now, actually, as I mentioned, that from our community, from Robert, me, and Adam, we normally at the very end, we just give one very common question to our invited speaker. And then we just try to share your view with our audience, because our audience are mainly PhDs and postdocs. What I found that both of you work both homogeneous as well as heterogeneous. So I think both of you are the ideal person to deal or to tell about these things. Obviously, both homogeneous and heterogeneous has their advantages and disadvantages. So to avoid that, nowadays, some people have developed, let's say, supported heterogeneous catalyst, which behave to some extent homogeneous. Or nowadays, I think we partly heard it from Dirk, actually, that single atom based catalysis to solve that issue, that it can be heterogeneous. And we can get the selectivity as well, like homogeneous. Of course, it depends on the situations. Like in some cases, it's good, some cases it doesn't bad, but more or less, these are the two methods. So what will be your opinions about, let's say, to improve these situations? that we can get a better catalyst which can be recyclable as well as which can be selective as well, like a homogeneous catalyst. Is it?
You, Shannon.
Okay, Shannon, please. What will be your opinion or views?
I don't think there's any one right answer, right? Because everything is dependent on the context.
Sure.
In general, I've never been overly keen on things like putting tethers on molecules and appending them to the surface, because in some ways you start to get the worst of both worlds, because they're often not that much more stable. But even that's an inappropriate claim, because I think there are cases where just site isolation could have benefits. The problem is if you so over-engineer. I mean, I saw Dirk on one of his slides said, one of the problems with one of his MOFs was that the linker was, too expensive. And, so the more you engineer something, like the copper tempo system is a case in point. Should we try to heterogenize the copper, to prevent copper agglomeration, which is probably, we don't really know, the source of decomposition? Yeah, maybe we should. Is there going to be a huge advantage in doing so? Well, you got to make sure you got the redox potential right. So there's going to be a whole science around that. And B, in the end of the day, once you've engineered your heterogenized copper, you're still going to have molecular tempo. And yes, there are people who've tried to put both together in the same construct. But at the end of the day, copper's cheap, tempo's cheap, and the way it's being used is you can combine cheap things and then dispose of what you don't need. And so you kind of have to know the problem, where the solution resides. So there's certainly going to be cases. I think Dirk's system is one of the most beautiful cases of taking what looks like a molecular catalyst and heterogenizing it, because the engineering is eminently simple, right? I mean, it's one of the most beautiful heterogenized catalysts you can find, by virtue of you're not putting in some sort of extract ligand or something into the system. It's taking advantage of bricks. So I don't know if that answered your question, but
no, we just wanted to have your view. Yeah. Thank you, Shannon. Dirk, can you please also say something?
Yeah, I agree. Yeah, obviously, it depends on. It mainly depends on the scale of the reaction that you're looking at, and whether this is an API for which you can afford to pay a high price in each step, or whether this is more large-scale chemistry. That's, I think, that's the main driving point. It's cost and what is the scale of the molecule that you want to produce. If you're going to make solid catalysts for reactions that are hyper rare, that you never encounter, or that very specialized, I don't know whether it makes so much sense. Of course, there are toxicity issues. You have to make sure that that your product is not contaminated by something that you really don't want. And like many years ago, we worked on a heterogeneous version of the osmium chemistry, to name one. There is a point, because I think every industry that ever wants to do a dihydroxylation still struggles with that, still struggles with the osmium. And let's say that our solution was reasonably involved. I mean, it was not too complex organic-wise, but we needed again then to modify an inorganic solid with some organic linker molecule, and it worked fine. Yeah, I think there is no clear-cut answer to your question, Ashobik, but I think it's important to make researchers, PhDs, postdoc aware that they should think about the application always. And you don't know when you start, but after a couple of years, you know whether it's industrially relevant or not, and so on. Toxicity of reactants is another one. If somehow you can develop reactions that avoid you to avoid the use of very toxic chemicals, fine. That's also one of the ways to go. It's as important as immobilization of the metal ion.
Yeah, thank you, Dirk, for your views, sharing your views. With this, then actually now we would like to thank both of you, both Shannon and Dirk, to share your time, to share the chemistry, beautiful chemistry. We have learned homogeneous catalysis, and then we have learned how to make homogeneous catalysis to make it a heterogeneous, and then to earn the excellent selectivity. So overall, we are, I would say, very much happy to to learn all this chemistry. So thank you very much for your time. Maybe Robert.
Thanks to all of you for listening.
Yeah, thank you.
Thank you.
And then we wish a very nice day Very nice day for Shannon. Nice evening for Dirk. Hope that in 2022 we are gonna meet together in by person actually.
Somewhere.
Yeah, somewhere.
Good.
Okay, thanks again. Bye-bye.
Yeah.
Thank you.
Bye-bye.
Bye.
Bye-bye.